I think title slide you can share first of all.
Fazlum, one thing to confirm, will you take questions in between or after some point of time should I interrupt you?
Hello. Yeah. The thing is like, so since they may encounter some problem in between. I mean, since these are like calculations, so maybe we can take questions in between if they are not too much. Let's see.
Okay, okay.
We don't need to wait. Okay.
So, Sayuri, can I make an announcement?
Yes, ma'am. Please go ahead.
Okay. So this is for all the participants. So this is to remind you that at 5 p.m. after the last session, we are planning a question and answer session with professors, with the lecturers who gave the talks. So you can ask questions. And I think judging by yesterday, day before yesterday, I had asked people whether they are interested, and based on that response, we are organizing this. So those of you who are interested, please stay on, and those who are not interested can log out. Okay. Harry, over to you.
Okay, so it's already 2:30 and 127 participants are there. So maybe we can wait for one more minute and we can start the session. So in today's session will be a joint session by Fazlur Rahman and Professor Shubinoy Das. We heard Shubinoy sir in the morning session, and Fazlur is a PhD student at IIA. He is working on observational cosmology. So maybe we can start the session, Fazlur.
Yes. So, Shairi, can you please announce about the tutorial problem set that students?
Yeah. So there is an announcement. There is a tutorial problem set which is given in the summer school website, and I'll just post the link again. Yeah. So yeah. Fazlu, you are good to go, I think.
Sure. Yeah. Hello, everyone. So good afternoon. Yeah, so I hope this would be one of the last sessions of this 1 week long summer school. I hope I'm audible, right, Sherry?
Yes, you're audible.
Okay, so as it is announced just now, so we have a set of problems that we're going to do in this 1 hour session. So this problem set is given in our website. So I hope you people have downloaded it. So we have around 4 to 5 questions. So we will try to do these calculations, problems one by one. So I hope that, okay, in the morning session, we have got 2 wonderful lectures by Shubinoy and Ravi, covering both theoretical aspects as well as observational part of cosmology. So, this tutorial session, I hope will complete the discussion. So the plan is like this. So we have 5 problems here, and I'll be doing, since the actual thing about problem in tutorial session is like people are supposed to come to Blackboard and do it, but here in this virtual platform we cannot do it. So unfortunately I'll be doing the calculations, and in between, if you come across any doubt or any clarification, you can write it in the chat box. And if time permits, after these 5 questions, then Shubhra is here and we can continue the discussions if you people have any doubts related to cosmology or the whole universe in general. So I hope you people have downloaded the questions by now. So yeah, maybe we can start. So let me read the first question. So we have used continuity equation to show how the universe have gone through different phases of radiation, matter, and dark. But remember, the continuity equation is inbuilt in GR, which are the Friedman equations, 2 Friedman equations which you have already seen. So now Friedman equation, using the first and second Friedman equation, which is already shown by Shubinoy, we can derive the continuity equation. So as Shubinoy has already told in the morning session, so we are going to derive it now. So the continuity equation is given here. So what Shubinoy has shown in the morning session is how the density of various components in the universe in various epochs, how is it evolving with respect to time using this continuity equation. Okay, so I'll try to solve it. So let me write the two Friedman equations. First one is A dot by A square plus K by A square is equal to 8 by 0 by 3. So in my entire calculations, I'm keeping C is equal to 1 for simplicity, but whenever we do proper numbers, we will bring back the value of C to be 3 into 10 power 8 kilometer per second. So this is one equation, and the second equation is A double dot by A is equal to minus 4 pi G by 3 rho plus 3p. Okay, so our aim is to get the final equation, which is rho dot plus 3h rho plus p is equal to 0, where rho dot is del rho by del t. Fine. Now, to come to this equation, what we have to do is we have to take a derivative of this first equation. So when we take the first derivative of this equation with respect to time, so what we will get is, I'm simply writing it here, to A dot by A times A double dot by A. Okay, you people are supposed to follow me, and you people, if you want, you can continue your derivation and we can finally match with my result and yours. But if you're stuck, you can just write in the chat box. So yeah, A double dot by A minus A square A dot, and there will be, I have to take a derivative of A again, plus K, then I'm taking the derivative of 1 by A square, so which is minus 2 by A cube is equal to 8 by G by 3. They are all constants. Then we have a derivative with respect to rho, which is rho dot. So I'm just writing it here, taking derivative with respect to time. Okay. So just for convenience, I'm giving numbers for my equations. So 1 and 2. Now what we have to do is, I'm just rewriting it again. So these two A dot by A, so A dot by A we know that is H. So I'm just writing it as H, A double dot by A minus, then again have A dot by A square minus 2K by A cube. Okay, there is a dot here.
Yeah.
There is a dot here. So A dot is equal to 8 by G by 3 rho dot. Fine. Now what we have to do is, so I can isolate this A dot by A cube as A dot by A times 1 over A square. So from this, from this all three, I can take A dot by A as a constant. So what I will get is 2 times H A dot by A minus A dot by A square minus 2K by A square. Sorry, if I'm taking 2 outside, then this 2 will go. So K by A square is equal to 8 by G by 3 times rho dot. Okay, so now things are clear. So we have equation number 3 here. So when we go back to equation number 1 and 2, so whatever I have in this bracket, they are just equation 1 and equation 2 only. So the A double dot by A is given by equation 2, and minus of some A dot by A square plus K by A square, that is what is given by equation number 1. So I can substitute equation 2 and equation 1 in equation 3. So finally what I will get is, I'm just writing it here, 2H, what are they? Minus 4 pi G by 3 rho plus 3p. Then I have an overall minus sign here, 8 pi G rho by 3 is equal to 8 pi G rho dot by 3. I hope you people are following. So many things are common here. We can cut some of them. So there is a 2 here, there is a 8 here, so it will become 4. Then there are many 3s here. I'm just cutting them. There is a pi pi g, these are all cancelled. So after all these cancellations, finally what I get is h minus this 4 I have kept like that. So 4 rho minus 12p minus 8 rho is equal to 4 rho dot. Okay, so now things are getting simpler. So I can, this will be minus 12 rho minus 12p is equal to 4 rho dot. So it's straightforward. I can take this 3 outside, I can cancel with this 12. So what is left is 3h minus rho minus p is equal to rho dot. Okay, so this is nothing but rho dot plus 3h rho plus p is equal to 0. Or in other words, it is the thing given in the question. 3 rho d rho by dt plus 3h p plus rho is equal to 0, which is the continuity equation. Okay, so from this continuity equation, we can obtain how, we can see how this rho is changing as a function of time. So if you remember, I can write what Shubha has written in the morning. Rho is falling as a cube for matter dominated epoch, and rho is falling as 1 over 8 to the power 4 for radiation dominated, and rho is a constant for dark energy dominated. Okay, so these three things were shown in the morning, and I think he was showing it for a general equation of state omega. So yeah, so that's about first question. So if there are any doubts or any steps which are not clear, you can ask me. Shadi?
I see no message in the chat.
Okay, fine. Is there anything in the YouTube?
Is there anything in the YouTube?
Okay. So I hope these steps are clear. It's straightforward. People can work it out. Maybe I can share these notes also with you in the end. So that's about the first question. We will move to second question now. So second question is, using FRW metric and path for a photon traveling to Earth from a distant object, where we have ds square is equal to 0 for a light or photon, derive the relation between scale factor and redshift. Okay, so I'll write the relation here. So I remember when Ravi was discussing the observational part, so he was showing you A by A0 is 1 by 1 plus z, where A0 is the current scale factor and A is at some particular z. Okay, so this is what we are supposed to derive. Okay, so z is the redshift. Okay, so again, for discussing this, we have to start from the very basic thing, which is the metric and line element, which is defined for the basic FRW cosmology. So, and we are tracking the path of a photon. So we have to see what will happen to the path of a photon and how it is represented in the metric. So the general FRW metric is given by now you might have seen these equations many times, minus c square dt square plus a of t, sorry, a square of t, dr square plus r square d theta square plus r square sine square theta d phi square. So this part is simple. This is the simple spherical polar coordinate system, and we have a scale factor a of t, which denotes or which quantifies the expansion of the universe. So we are not interested in the exact value of scale factor, but we are interested mostly in the relative difference in the scale factor. Okay, what is the scale factor now with respect to at some epoch? Say, what is the scale factor at the, I mean, relative to current at the time of CMB, or I mean, different epochs in the universe. Okay, so this is the starting metric. Now for a photon, we know that the line element ds square is equal to 0. So what we are doing is, so this redshift, which have been discussed in the morning lectures, we are trying to calculate the redshift in terms of the scale factor. Okay, so d square is equal to 0. And second thing is that it's photon, so it will always travel in straight lines if there are no gravitational lensing or other complications. So in that case, we can assume that these photons are coming to us radially. So which means that d theta is equal to d phi is equal to 0. So my metric is now very simple. It is 0 is equal to minus c square dt square plus a square of t dr square. So this is the simple metric that I have. So now my interest is, okay, one more thing that I want to stress here is, so in the general metric that Shubham was showing, there is a 1 minus kr square term here. But for simplicity in our case, and we know that our universe is like this, k is equal to 0, which is the flat case. You can do the same calculation with k equal to non-zero also. It's not a big complicated thing, but just for making our calculation simple, we are just keeping k equal to 0, which is the actual one. So this is the metric. Now my interest is, so let's consider a source at a distance r from us. Okay, so let's assume that there is a galaxy here and we are here. So the distance between this is r. Okay, so galaxy is here, observer is here. So just for simplicity, it is denoting it as E, which is the emission, and this is observation. So to note that this r is a co-moving distance. So by now I hope that you are clear with the idea of co-moving distance, which is the constant. So under expansion, co-moving distance is not going to change. Okay, so r is the co-moving distance between us and the source galaxy. Okay, so let's consider a source. So when there is a light source, light will be emitting from them. So now we can just rearrange this equation number 1 as follows: dr is equal to c square. Yeah.
There is a question.
Yes.
Can you explain why the metric for the photon is 0? Like what is
okay, so this comes from special relativity. So from special relativity, we know that so if there is any particle, so we use it as representing the metric. So this is the time coordinate and this is the spatial coordinate. Now we see that light always travels in this along the boundary of the light cone. So which means that ds square is equal to 0 there. Okay, so for a photon, so this is the postulate of special relativity, that the line element for a photon is always equal to 0. So the special relativity is constructed based on that. Okay, so since GR and cosmology are the extension of special relativity, so this thing is applicable there also. Okay, so I hope that is clear. So now dr is equal to okay, this is c dt by a of t. So I can say that if this dr is the small elemental co-moving distance and dt is the small time. So in order to get the whole r, what we do is we integrate it. So when I integrate, I have dr is equal to integral c dt by a of t. So what I'm going to integrate here, so we are just considering that there is a pulse of light pulse is coming, which is emitted at a time te and which is observed at a time to, or I'll use t observed. And this dr is, so this is from 0 to r. So I have 0 to r. So just for sake of convenience, I'm keeping dt prime and such that this is not confused with the limits. So so this is the case for a first pulse of photon. So the idea is we are considering a photon pulse coming from a galaxy source, and it is emitted at a time t and it is observed at t observed. So this is the equation. So this is given by, this is r. Now what will happen at another small time, delta, after delta te, what will happen is another pulse will be emitted. So if there is a light source, there will be multiple pulses. So these pulses can be seen as the crests or troughs in the standard classical electromagnetic case wave picture. So it's like pulses are coming. So after delta TE time, there is another pulse coming, and it is observed at delta TO time. Observed. Okay. So about that pulse, I can again write R is equal to 0 to R dr prime, which is not going to change, but the limits of the second part, which is TE plus delta TE, which is the time at which the second pulse is emitted, and T ops plus delta T ops dc dt prime by A of t prime. So I'm giving this equation number 2, and this is equation number 3. We know that within the LHS, which is R, which is the entire co-moving distance, this is not going to change, right? But we are only interested, or the RHS part is different, but LHS part is not same. Is same. So when LHS in both these equations 2 and 3 they are same, the RHS will also be going to be same. So what we can write is T emitted to T observed C dt prime by A of t prime is equal to, I'm simply equating the RHS. So TE plus delta TE and T ops plus delta T ops. See, dt prime by A of t prime. Okay, so this is equation number 4. Now, just following the geometry, we can rewrite the limits. So the limits can be rewritten as T emitted to T emitted plus delta TE C dt prime by A of t prime is equal to T observed plus delta T observed C dt prime by A of t prime. So now we are taking an assumption that this delta T is very small, such that this A of t is not going to change much. So the picture is clear. So there is a galaxy source, it is coming, so waves are coming. So first one is the first pulse, and second one is the second pulse, which is coming after a time small duration delta T. So within that small time, A of t is not going to change. So with this assumption, what we can do is we can do some Taylor expansion here. So this Taylor, I'll do it like this. So if A is equal to the integral C dt by A of t, then after applying the limit, what I will get is A of TE plus delta TE minus A of TE is equal to A of T ops plus delta T ops minus A of T ops. Okay. So since this delta T, yes.
Can you explain equation 5 again?
Okay, equation 5. So equation 5 is the question is like how we get from equation 4 to equation 5?
No, just explaining it very briefly.
Okay. So what is TEM? So this is the time at which the pulse is emitted. Okay. So this first pulse is emitted. Now after some time, there is a second pulse is emitted. So after a time of T emitted plus delta TE, a second pulse is emitted. Okay. So now what is T observed? This is so we are here as an observer. So we are receiving the first pulse at T observed and the second pulse at T observed plus delta T observed. Okay.
Okay. The confusion is between how we come from equation 4 to equation 5, I think.
Okay. So that is simple geometry. So maybe I can draw it here using a different color. So you can think of it as like this integral is like a TE plus delta T. So what I'm writing it is the equation 4. So TE we are integrating from TE plus T observed, and here it is TE plus delta TE and TO plus delta TO. So if we say that these two are same, then this region will also be same. So that is the idea. You can think of it, and it's there is no complicated mathematics or anything, cosmology there. So it's basic integration. So this limit is working. Okay, so I hope that's clear. So maybe later, if you have further clarification, we can discuss. So that's all about this. Now I'm doing a Taylor expansion. So when I do Taylor expansion around TE, so I have a of TE minus, sorry, plus delta TE del A by del T at TE minus A of TE is equal to A of TO plus delta TO A by del T at T equal to TO, sorry for the less space, minus A of TO. Okay, so I can cancel A of TE, A of TE, A of TO, all these things. What I'm left with is delta TE by at TE is equal to delta TO A by del T at TO. So del A by del T is what comes inside the integral, right? And that is at T0 or TO and TE. So this will equivalent be delta TE by A of TE, which is what comes inside the integral, is equal to delta TO by A of TO. Okay. So up to now, I hope things are clear. So let me explain this. What is delta TE? Delta TE is the time interval or gap between the first and second pulse emitted. Now, what is delta TO? It is so we are observing it. So delta TO is the time interval or time gap between the observed first pulse observed and the second pulse observed. They are not going to be same. They are not going to be same if you have this A. If both A, TE and TO, if they are same, then they are going to be same, but that's not the actual case. So the point is that even though there are two pulses emitted and if they are received after some time, so the time gap at the emission is not equal to the time gap at the observation time. Okay, so what does this imply? So we know that the gap between two pulses, so this is actually what is frequency of a wave or a wavelength of a wave, etc. So we usually write delta T is inversely proportional to 1 over nu E, and delta TO is inversely proportional to 1 over nu O. So we usually say that, right, for a wave, the difference between two crests or two troughs, that is actually the wavelength, or I mean, if it is in terms of time, it is the frequency. So delta TE and delta TO, they are related to the observed frequency and the emitted frequency. So now I'm rewriting them here. So let me, I don't know if what is the equation number, maybe this is equation number 5. So this equation number 5 now becomes 1 over nu E by 1 over nu O is equal to, I'm just rearranging it, A of TE by A of TO. Okay, so if I bring it ulta, so nu E by nu O is equal to A of T observed by A of T emitted. Okay, so the picture is like this. So there is a galaxy and we are sitting here. So galaxy is here, observer is here. So at the emission, at the time of emission, the scale factor of the universe was A of TO, TE. Now at the time of observation, it is TE. So if there is a difference in the scale factor, which means that if the universe has expanded by this time, then we will see that there is a red shift or a blue shift in the wavelength or the frequency of the emitted light. Okay, so now we have to
Fazlu, at the observation it is AT not TE. The value of scale factor. At emission it is AT. In both cases you have written ATE.
did I make
That would
this?
be
Is E. This is E. Okay, here.
with T not.
Okay, clear. Okay, clear. We see that if there is an expansion of the universe, then the frequency of the emitted light is going to change. Now we want to see whether it's a blue shift or a red shift. So for that, what we have to see, we need to check whether nu E is greater than nu O. So we know that the universe is expanding, which means that ATO is always greater than ATE. Okay, which means that nu E is always going to be greater than nu O, or in other words, nu O is always less than nu E. This implies that there is a red shift in the emitted light. Okay. So now just to make things in terms of redshift, so usually we define redshift Z is equal to nu E minus nu O by nu O. This is the usual definition of redshift, which is the rate of change in the relative change in the frequency. So 1 plus Z is equal to nu E by nu O. So now substituting back in our main equation, which is equation number 6, what I will get is 1 plus Z is equal to ATO by ATE. Okay, so this means that there is always a redshift if there is an expansion of the universe. So now usually the convention is, so since we are here and we are observing, the current value of scale factor ATO is taken to be 1. Just for simple, that's the convention, and it makes things simpler. So now I can write 1 plus Z is equal to 1 over ATE. So there is a one-to-one relation between redshift and the scale factor. So now we can ask, what if the Z is equal to, at the time of CMB emission, Z is equal to 1100, what is the scale factor? You can ask. So when I say what is the scale factor, so what is that? So that is the relative size of the universe with respect to the current one. So this will come almost around A0 by AE. ACMB is of the order of 1100. So which means that at the time of the emission of CMB, the size of the universe was 1100 times smaller than the current size of the universe. So that's all about second question. So if there is any doubt, you can ask. If not, we can move to the next question.
Yeah, Fazlu, there was a question from YouTube by Keval Chetri. He asks that does only photon follow null geodesic, or is it true for all massless particles?
All massless particles will follow the null geodesic.
Okay. Yeah, there is no more question.
Okay, sure. So now coming to the third question. So the third question was about dark energy. So Shubham was showing in his lecture that the current observed value of dark energy is 10 to the is equal to 10 to the power minus 120, smaller than the value predicted from theory. Okay. So, and he has introduced the idea that, okay, there is an epoch where the currently dominated dark energy, so its density was equal to the density of matter. So we have actually 3 epochs. So basically 3 epochs. If you include inflation, there will be more. But we have radiation dominated epoch, we have matter dominated epoch, and we have dark energy dominated epoch. So what will happen is here things will fall as is equal to rho 0 by a to the power 4. Here it is rho 0 by a cube. Now here it is rho is constant. So dark energy density is going to be constant. Now there will be always an epoch where the density of dark energy will be equal to density of matter, and here density of matter will be equal to density of radiation. So the idea is how to find out the epoch at which the radiation density is equal to matter density, or matter density is equal to dark energy density. So in this question, we are asked to calculate the epoch or the redshift at which the dark energy density is equal to matter density. So it's quite simple. So what we do is we simply equate. So we equate rho dE is equal to rho m, which is the matter density. But we know, no, we need to write it in terms of the current values. We don't know what was the value, but we are not going to measure it at that epoch. We are doing the observation here, and we are trying to extrapolate. So at current, in terms of current value, so I denote current value of rho 0. That for dark energy, that's not going to change because it's a constant. So this is at a particular redshift is equal to dark matter. So for the matter, this is rho m current value by a cube. But simply, just now we have seen that 1 over a cube, I can write it as is equal to 1 plus z cube, because 1 over a is 1 plus z. So this is the case for the dark energy. So now what we are doing is like, so we can find out a z for which this value is valid. So this density of dark energy is equal to density of dark matter or dark matter. So I'm just keeping this as equation number 1. So when you substitute it here, so we know the value of rho dE now, we know the value of rho m now. So once we substitute it here, what we will get is z is equal to some 0.55. So at this particular z, the density of dark matter, or dark matter is equal to dark energy. So okay, so far things are clear. So this is the current value that we know where the transition happened between matter to dark energy. Now the question is, what will happen if the fine-tuned value 10 to the power minus 20 is not the actual value, but there's a different value? Let's say, so Shubhana has given the value as 10 to the power minus 117. So what will happen at that case? So in that case, our value of rho 0 dE, we are substituting it here. So this is, I'm just denoting the new dark energy value as a prime. That will be equal to rho 0 m by a cube. So I'm just rewriting the equation number 1, but with the new dark energy value. So is equal to rho 0 m by 1 plus z prime. So because of the new dark energy value, dark energy density has changed. So the epoch of equality of the density, this is going to be different. So I'm denoting it by z prime is equal to 2. So I have both equations, equation 1 and 2, divide. Okay. When I divide both, what will happen? Rho dE prime by rho dE is equal to, simple division, 1 by z cube by 1 plus z. Okay. So now we know what is rho dE prime by rho dE. So this is 10 to the power minus 117 by 10 to the power minus 120 times rho dE theory. Here also it is rho dE theory. So these get cancelled, and what I'm left with is 10 to the power 3. Okay. So this ratio we know, just substitute it in equation 3. So equation 3 now becomes 10 to the power 3 is equal to 1 plus z prime cube by 1 plus z cube. We have cubes everywhere, so it is 10 is equal to 1 plus z prime. I'm just writing this here, 1 plus z. So now we know z is equal to 0.55. There will be some correction, but for the time being, let's keep it 0.55. So it is 1 plus 0.55 into 10 is equal to 1 plus z prime. So this is 15.5. 1 plus 0.55 is 1.55 into 10 is equal to 1 plus z prime. Now, what is z prime now? Z prime is 14.5. Okay, so you can see that. So when the observed value was 10 to the power minus 120 times the theoretical value, the epoch at which matter density was equal to dark energy density, that epoch was z equal to 0.55. Now, when I change that observed dark energy density, that fine-tuned value, to a very small difference, it's not actually small, it is 10 to the power 3 times smaller, larger, then what will happen is that the new epoch at which the density of matter is equal to the density of dark energy, this is 14.5. So what does this mean? So this means that after z prime is equal to 14.5, the universe is dominated by dark energy. Okay, so the second part of the question is, can life form on Earth if this is the case? Of course, no. Why? The thing is that we have seen, so in both the lectures, it was discussed that the structure formation was happening around this time. So to form the structures, there should be gravitational collapse. And we know the nature of dark energy, which is accelerating. So the expansion is there. So if dark energy is dominating by that moment itself, which is very earlier than the one with 10 power minus 20, structure formation won't happen. And there won't be any gravitational collapse such that whatever we see as structures, as galaxies or stars, this won't happen. So we can see that only if the value is of the order of 10 to the power minus 20, we can have an epoch where dark energy is dominating, which is favorable with the structure formation. Okay, so yeah, that's about question number 3. Now, if there are no questions, I'll go to the next question. Shari?
Yeah, there are no questions right now.
Okay. Yeah. So now question number 4. Question number 4 is about the rotation velocity. So we are asked to calculate the rotation velocity. Yeah.
First of all, just to interrupt you,
yes.
There is a confusion. Shouldn't there be cubic powers in equation 2 and 3? Could you clarify that?
I didn't hear you. Can you repeat the question?
Yeah, the question is maybe a typo. There should there be cubic powers in equation 2 and in equation 3?
Equation 3, sorry, yeah. There is a cube here. There is a cube here, yeah.
Okay, thanks.
Okay. Yeah, now. Okay, so now we are trying to get the expression for rotation velocity using Newtonian equations. So we know that we'll start with the basic Newton's law. So we have gmm by r square. Now, if this is balanced, so if the centripetal acceleration is balanced by the Newtonian gravitational acceleration, we have the basic equation mv square by r. Okay, so the question is to obtain the expression for rotation curve as a function of the radius. So the idea is simple. So we have the gravity. So there is a galaxy. So most of the masses. So the center of mass is approximately at the center. So, or at least we can say that in the common center of mass, all the systems or the stars, they are rotating, or all the gravitational bodies, they are rotating. So as we move away from the galactic center, so that distance is denoted by r. Okay, so now there is a boundary. So this boundary, I'm marking it as capital R, which is the which can be considered as the visible boundary. Okay, so now what happens is what we are asked to calculate is we are asked to calculate how the velocity is changing as a function of r. Okay, so we are asked to show it in the case of a homogeneous density. So when we say it is homogeneous and spherically symmetric, we can take the density of the matter inside this any circle as a rho of r is constant. It is not a function of r. So using this basic thing, okay, just before that I'm cancelling this all small m's and one r with another r. So what I will finally get is v square is equal to g mr, which is the mass enclosed, by r. But this mass enclosed, so we can actually write it in terms of density. So g by r is equal to rho of r dq bar. Okay, so but we are given that rho r is not a function, so it's a constant as a function of time, as a function of radius. So I can take rho outside. So what is left is v square is equal to g by r rho, simple dq bar, which is the volume of the given given halo or given spherical surface. So it is G by R rho 4 by 3 pi r cube. Okay. So I'm not explaining much because these are straightforward calculations. So this is G rho 4 by 3 pi r square. So there are many constants here. Okay. So rho is also a constant. So we can write v square is proportional to r square. So the rotation velocity v square is a function of r is directly proportional to r square, or v is directly proportional to r. So when is this applicable? So this is applicable when the density of the matter inside the galaxy is uniform. Okay, so this is uniform until the total size of the galaxy or total radius of the galaxy. So this is applicable only up to v is directly proportional to r, only up to r is less than or equal to r. Okay, now what will happen outside the galactic region? So let's say the visible disk. So what will happen is that we can simply use the equation v square is equal to gm by r. So the entire mass is involved in it. So now it is not a function of m. M is not a function of r because the whole region is enclosed. So we can get v is equal to 1 over r to the power half. Okay. So now, so this is for all r greater than capital R, which is the boundary or the edge of the galaxy. So when I plot this, the rotation velocity, so what I will get is, so this is v as a function of r, and here this is r. So I'm denoting this as my region. So if I plot this, what I will get is, so in the initial region, I'll find an increasing r is v is increasing as a function of r linearly, and then from some point it start to fall. Okay, so it will fall and go. Okay, so this point is the edge. Okay, so this is the expected from Newtonian cosmology. This is the expected relation for the rotation velocity. So here it is r, and here it is r to the power minus half. Okay, so now when we do the actual observation, we don't find this. We see that from here also this is actually a constant, or it is increasing. So this is what demands us to introduce the idea of dark matter in the galactic scales. So yeah, that's about that question. Now coming to the fifth question. Okay, so if you have any further confusion about dark matter and the rotation curve, we can discuss. So yeah, so now I'll quickly go to question number 5. So question number 5 is actually to compute the distance to last scattering surface. Okay, so what is last scattering surface? So that is the surface from which CMB is emitted. Okay, so we know that CMB emission happened at Z is equal to 1100. So these are, okay, 1100. These are the basic numbers that we have to keep in mind. So from that surface, the CMB is coming towards us. So this emission is happening even now. And this last scattering surface, its size is also increasing. Okay, so so this fifth question is, so the motivation of this fifth question is to give you the idea about particle horizon, even though the particle horizon is not exactly the distance to the last scattering surface, because there is a small correction to it, but we will try to derive it. Okay, so again, for doing this derivation, yeah, we have to we have to start with the metric, basic FRW metric, and then we have to track the trajectory of the photon. Okay, so before that, I just want to tell you something that I have missed in the first question. So we don't know. So we know that we have radiation dominated epoch, we have matter dominated epoch, we have dark energy dominated epoch. I don't know if it was shown in the morning session how the scale factor is evolving with respect to time. So how is this? So whether it is a linear one or whether it is a cubical one, so we have to obtain that. So the evolution of scale factor as a function of time. So it is given by the Friedman equation, because Friedman equation is the equation which governs the dynamics of the expansion. So we'll start with it. So it's not a tedious job. So I will show it for show it for radiation and matter, and I will ask you to calculate it for dark energy. So I'll start writing A dot by A, which is the Friedman equation. First Friedman equation, A dot by A square is equal to 8 by G rho by 3. So if you remember, there is a K term, but K by A square, but for the time being, again, I'm keeping K equal to 0, because we know that the universe is flat from observations. So I have A dot by A square is equal to 8 by G rho by 3. Now what will happen at the radiation dominated epoch? So at the radiation dominated epoch, we know that the density of the universe is falling as 1 over 8 to the power 4. So I can simply substitute it here. So A dot by A is equal to 8 by G by 3. So just to remove this, you can write, so just to remove the proportionality constant, I have a constant here, which is the current size, sorry, current density. So yeah, now rho 0 by 8 to the power 4. So what will happen is, so this is like A dot square by A square is equal to, I'm just keeping all these constants to be C times 1 over 8 to the power 4, where C is 8 by G rho 0 by 3. Okay, so I can cancel A square with this, and now what I will have is A square. So C into 1 minus A square is A dot square. Okay, so now you can bring, so this is dA by dt square is equal to 1 over A square. Okay, so dA by dt is equal to 1 over A. So this can be taken as A dA is equal to dt. So okay, I have missed the constant here. The C is always here. So A square by 2 is equal to okay, C A dA. Sorry, C dt. Okay, I don't want you people to confuse this capital C with the small c, but this C is the constants. So A square by 2 after integration. So maybe I'll write it here. A dA is equal to integral C dt. So after integration, this is A square by 2 plus some constant is equal to, since we are only interested in how time is evolving, how time and scale factor are related. So I'm writing it CT. So we can see that A is now, so these two can also be absorbed. So this is A square is equal to some C prime times T, or in other words, did I make any mistake here?
It's okay, because it goes as t to the power half.
Yeah.
So A goes as t to the power half.
Yes, it's clear. So A goes as T to the power half. Okay. Now, since we are running out of time, so I'm not doing it for matter-dominated universe. So for matter-dominated universe, what we have to do is we have to take matter-dominated universe. It is A dot by A square is equal to 8 by G rho 0. Here we have to take A cube. So when we take A cube, then finally what we are supposed to get is A is T to the power 2 by 3. Okay. So
and you can also write the answer for dark energy.
Yes. And for dark energy, we don't have any. So this rho is always rho 0, which is, it doesn't have any scale factor dependence. Because of that, A can be is equal to e to the power some rho 0 time t. So you can see that when dark energy is dominated, or when dark energy is only there, that is the actual thing, we can see that there is exponential expansion, so which is one of the cases that we see in inflation. So these two are homework. You can work it out, and if you don't get, you can write to me. Now coming to the final question. So in the final question, we have we are actually asked to calculate the distance to the last scattering surface. So here also we think of it as like, okay, so there is a photon which is coming from the last scattering surface. So if I write the metric, so it is ds square is equal to minus c square dt square plus a square dr square. Okay, we are asked to calculate what is r, which is the co-moving distance. So for photon, this is equal to 0. So minus c square dt square is equal to a square dr square. So again, the starting equation, we will get it. So we have r is equal to dt by a of t, and there is a c here just for simplicity. Okay, I'm not keeping c as 1 because in the question it is coming. So we have d of t as a function of a, dt by a of t. We are integrating it. So this is the co-moving distance. Now, so what is the, to what co-moving distance are we doing? So we are interested in for a light which is traveling from t cmb to t0. Okay, dt by a of t. Okay, now we don't know. So we know that. So after the emission of CMB, the universe is mostly matter dominated, but very recently it became dark energy dominated. So what we are doing is we are assuming that the universe is mostly matter dominated, and we don't consider the dark energy dominated epoch for the time being. So to do the actual calculation, we have to include dark energy also, but just for showing the result, I'm assuming that we assume that universe is matter dominated. So with this, what will happen is a of t is directly proportional to t to the power 2 by 3. So which is the thing I just do. With this, just to remove the proportionality constant, I can write it as a of some t by a0 is equal to t of some arbitrary t by t0 to the power 2 by 3. Okay, so now substituting it back in our equation, so what we will get is c times dt, this is tcmb, this is current value, by this a0 we always take to be equal to 1, which is the current scale factor. So what I will get is t to the power 2 by 3 by t0 to the power 2 by 3. Okay, so this is c times, I can take this to the numerator, so c times to the power 2 by 3. Now I have an integral. So there will be this thing 2 by 3. Okay, so this integral can be worked out. So this is tcmb and this is t0. So what will happen is, so t0 2 by 3. So this integral is very simple. So this is t to the power 1 by 3 from tcmb to t0. Okay, so this is ct0 2 by 3. Okay, I have already missed one number. So this is 1 by, when I do the integration, there will be a 3 coming here. So after the integration, so into t0 1 by 3 minus tcmb 1 by 3. Okay, now we will come to, so what we are calculating is the co-moving distance to the last scattering surface. So now we will check the numbers. So we know c, we know t0, we know tcmb. So t0 is approximately 1 billion year to the power 9 years. Now tcmb value is given 0.3 mega years. So it is tcmb is 10 to the power 6 years approximately. So my point is that if I subtract this huge billion year to the power 1 by 3 minus this, so this is a very small number. So approximately I can write 3c t0 2 by 3 times t0 1 by 3. I can neglect the second part. So what is this? So this is r is equal to 3c t0. This is 2 by 3 and this is 1 by 3. So this is 3c t0. Okay, so what I have obtained here is the distance to the last scattering, or to be very precise, so this is the current size of the current size of the particle horizon. So what is this idea? So this is like, okay, there is a photon which is coming from the early universe and it is traveling to us. So there will be a maximum distance that light or photon can travel, and that is the maximum. So that is the distance to which at max we can, and there could be the sharing of information or the region of causality, we can say, because by special relativity we know that, okay, only if photons are traveling or light is traveling from one point to another, then those regions are causally connected, or the information is exchanged. So as per the assumption that, okay, the universe is matter dominated, we find that the current size of the particle horizon, that is 3c(T0). But if there is no expansion, what we think of this particle horizon? So we think that, okay, there is the age of the universe is 13 billion years, or okay, 13 billion year. Now what is the light traveling distance? So we know the idea of light years, so this will be like c times T0 if there is no expansion. So if there is no expansion, then particle horizon is just CT0. But because of expansion, we see that even though it is not, it is so even though the photons have emitted, so the universe is expanded before the photon is reaching us, which means that we have a 3 times larger size of the particle horizon than what we have when there is no expansion. So this value of particle horizon is obtained by assuming that the universe is matter dominated. Now you can repeat the experiment as a homework I'm giving you. We can repeat the experiment assuming that the universe is radiation dominated, and you can calculate it, the value of particle horizon. So the question is, what is the particle horizon if the universe is radiation dominated? So if it is radiation dominated, where are we going to change? We are going to change this relation. So here we have used T to the power 2/3, but for radiation dominated, we have to use A is directly proportional to T to the power half. Another question is, we can calculate the particle horizon if the universe is dark energy dominated. Okay, so these two cases you can work it out, and you can see that the answer that we are expecting for this is 2CT0. That is also greater than the CT01. So if I remember correctly, this will come, this is an exponential one, so this comes around e to the power lambda T0. Shubhna, if I'm wrong, please let me know. For dark energy dominated, it comes to be exponential.
It will be some exponential.
Exponential, yeah. So you can check it and you can write to me if you have any confusions. So yeah, so that's all about. So within the given 1 hour short span, we are not able to cover everything, every aspects of cosmology questions, but yeah, so I hope we have covered some of them. So if you have any queries or doubts, you can ask.
You can upload this, no? This in as a PDF.
Sure. Yeah, this notebook I can upload in the tutorial section of the website. So yeah.
Thank you, Fazlu. It was very nice, because I suggest all of you to at least work on this little bit, then you get a sense all the 5 of basic cosmology.
Yeah, I might have done it in a very faster way because of the time constraints, but you can go through these notes and check every steps. And if you have any doubts or questions, you can either write to me. Yeah. So,
Thank you so much.
Shari?
Yeah, it was a very nice presentation and explanation, and I can see all the chats, and they are very much appreciating your effort.
I'm very much glad about it.
One request was there, whether there are any references that you can provide for these calculations so that they can work out later, or any other interesting problems they can work out later. So references for those would be really helpful.
Yeah, so if people have done GR, then things will be simple. If not, what I can suggest is the first 2 chapters of Dodelson will be easy. At least the first chapter will be easy. So, and the problem set there. Of course, anyone can try with little, so which is the very basic one. Even people are not without GR background can try the and2 littles modern cosmology. Shubhna, do you have any other suggestions? I don't know if they're around.
So there is a question from YouTube from Kostav Malakar. Can we combine contribution from matter dominated, radiation dominated, and dark energy dominated to calculate particle horizon?
Yeah, I think I missed to tell that. So in order to calculate the actual size of the particle horizon, we have to do the integral like that. So we have to, so you have seen it now. So what I have done is I have integrated it from TCP to T0, just assuming that, okay, everything is matter dominated. But the actual calculation to be done is like, okay, we have to start from the initial 0, T equal to 0. Then up to the time when there is radiation dominated, we have to use the A is equal to T to the power half relation. Second part, we have to use the matter one. Third, we have to do the dark energy one. So this complete integration that we have to work it out, and that is how to calculate the dark energy, the size of the particle horizon. So that is the proper way. You're right.
Yeah. So we can wait for 1 or 2 minute more if there is any pressing question.
Okay, I'll write the textbook name here and true details.
So I think there are no more questions for this session. So ma'am, you can take it here from now.
Okay, I have maybe two announcements. So one announcement is for the certificate. So we will check the attendance and then provide the certificate. So that will take us some time. So by July 30, we will email you the certificate. Okay. That's about the certificate. Then about the session at 5 o'clock today, several of the lecturers have agreed to be present to take any questions from anybody, any of the participants. So please use this opportunity, be there, and you can ask to any of the lecturers. And I will, of course, moderate the questions. I think that's all. That's all the announcements. So you can take a break now.
This attendance is shared in the chat box. Please have a look.
Okay, attendance is shared. Very important. Nice. The photo looks nice.
Yeah.
But yesterday, Crispin, yesterday there were around 230 people.
Yeah, still that
This
number is
looks,
visible in the one of the photo. Yeah, 234.
but this looks fewer than 200 MI. Is it an optical illusion?
No, I have counted close to that. For example, this is 12. One picture is 12.
Okay, okay. 12 into 5 into 5. Maybe a bit less. So I'm sure people have seen this photo in the website. You can download it from there. Okay, Crispin,
Yes.
can you please make Ebenezer the co-host?
Okay. Yeah, done.
Okay, Abby, are you there?
Prabha, I am here.
Okay. Shall we test whether?
Okay. You can check my video. Is it okay with you?
Yeah, we can see your screen.
Okay. Thank you.
Okay. So will you take 1 hour? You have 1 hour.
Yes, I have 1 hour, but I will try to shorten as much as possible. I like being the last session, last class in this one. So I would like to, I have a matter for 1 hour. Yes.
Okay. Okay, Aparna, I can see your question. You can give the feedback after the school is over. So, Crispin, if you can find Rajaguru, please make him co-host also. Shall we begin, Ebi? Ebenezer?
Yes, we can. Yes, we can begin.
Okay, so welcome to everybody for the last session of the school. The session now the session that we are going to have now will be an introduction to the Kodaikanal Solar Observatory, and we will be guided by Dr. Ebenezer Chelasamy, who is the resident scientist at the Kodaikanal Observatory. So he will take us through the various facilities, various views, and so on in the observatory. So Ebi, please begin.
Okay, welcome you all to Kodaikanal Solar Observatory. Am I audible? Okay.
Yes, you are audible.
Okay, wonderful. I think you can also see my screen, I think.
Yes, we can.
Okay. Welcome you all to Kodaikanal Solar Observatory on behalf of our director, Professor Annapurni, Dean, Professor Ishwar, and summer school coordinators, Professor Prabhavati, and scientific organizing committee. I thank you. I welcome you to Kodaikanal Solar Observatory. It is one of the beautiful place in the entire Western Ghats. We have some other beautiful places also, Kodaikanal and Yerkad and Ooty, Udagamandalam. These are the hill places there in Western Ghats. It's a very, very, very beautiful place. We are located at the altitude of 2,343 meters above the mean sea level. It is one of the beautiful places. And I just wanted to this is my brief overview. I just wanted to tell about what is Kodaikanal Observatory, what is historically what is stored here, and what is the research we are doing here. And I am going to take you through various departments virtually, and some of the important results what we have made here, and observatory and you, like at the end you will decide whether to visit this place, Kodaikanal. It's one of the beautiful places in entire stretch of Western Ghats. Okay, and Kodaikanal, our observatory is almost located 3 kilometers from the city, the town. We have a big lake is there, very beautiful lake, and opposite to our observatory we have a rose garden. One can spend easily 2 hours or so there. It's also a very beautiful place. And this is our entrance when you are coming to Kodaikanal Observatory, and you can see the board, Indian Institute of Astrophysics. And Kodaikanal, this place is also a wildlife reserve. We have a cluster of bisons. Wild bisons will be coming to our place every now and then. And if you are very fortunate, you can also see and make some photographs here. And we have a nice garden here in Kodaikanal Observatory. And we have the history for this place, we long back, it is starting from the 1786 according to our records. And the Britishers, when they wanted to come to India, they just identified they have to come only through the sea route, and sea route, it will be too tiresome. It will be so difficult also when you are going inside the sea route. Inside 200 kilometer or so, everything will look alike for you. Yes, except your guiding thing will be a compass will be there. For nighttime, people being trained to see the constellation and other stuff to identify the direction. And later it was some of the people like John Evershed and Mickey Smith and other people, they wanted to do some science along with their navigation purpose. So they brought their telescope from England and they have set up here at Kodaikanal. And already most of you know about Kodaikanal Indian Institute of Astrophysics. We have Kodaikanal Solar Observatory, Vainabhav Observatory, Radio Observatory at Gauribudinur, Agar high energy gamma ray astronomy. And recently, almost some few years back, we have launched the first satellite AstroSat, and the part of the UVIT, it is working very well. And of course, you all may be knowing about a TMT telescope, and the future is coming up with Aditya L1, the solar mission. Basically, Kodaikanal Observatory is a dedicated solar observatory. Of course, all the other branches we have at many other places of our institute. In the year 1909, January 5th, John Evershed published an important discovery. And to honor his discovery, Government of India, they released a stamp after 100 years of his studies. This is what you are seeing here. And this says that there is a radial flow of gases in the penumbra of the sunspot. And he is John Evershed. Very interestingly, he worked here. He stayed here in Kodaikanal. The instrument what he have used here, it's still there. It is in a good working condition even. And he was working on the sunspot. You must be knowing about the sunspot. It is a dark region in the solar atmosphere. Since the temperature is a little bit lower than the visible photosphere, it is moderately, it is cooler, it look very dark. And if you carefully look into the sunspot, you can see about umbra as well as the penumbra. Umbra is the darkest region. The penumbra is the surrounding region. He discovered there is a radial flow of gases from the internal regions of the penumbra. And he discovered the flow, it's approximately around 40 to 45 kilometers or so. That is now, it is turned as a Evershed effect. And this is the picture you are seeing. And this is also the original picture is there in our Kodaikanal Observatory. And there is a, as I already told you, there is a, he discovered there is a radial flow of gases across the penumbra of the sunspot. And we have a nice facilities with we have a very modern workshop here. We can whatever telescope repair and all the stuff we can do it here in this our workshop, and we are updating it every now and then. And if you have some ideas to do something, immediately you can draw the pictures, and if we can give it to our people, they will make that good instrument for you. So we have a capable team of band of people are here to help you. And one of the oldest telescope we have is came here to India in the year mid 1850s or so. And that was kept in a director's bungalow for some time. And in the year 1895, they brought it here to Kodaikanal. And Kodaikanal, they made a good dome and all the structures. Still, it is in a good condition. And every single day, we used to take an image from this one. And from the year 1904, we have a regular data or regular observations on the sun we have taken here. It will be, you can see the picture, it will be like this. And the images taken from this telescope, and it will be like this. And earlier days it was there in the glass plates, and photographic emulsion was there on the glass plates. Nowadays we have made all the stuff like now it is available in the plastic sheets. The photographic films are very expensive now. I think you may be knowing, like if acid and all the stuff, developing, fixing and all the stuff is a bit expensive, but still we are doing that. And this observations is available, this long-term studies of the sun, it's available still with us. And I will take you through different other places. And the left-hand side, you are seeing another telescope, that is 8-inch telescope we call, otherwise we can also call that as a Pogson telescope. And Norman Pogson, he worked here in Kodaikanal Observatory, and he was also a director, and he worked for almost 30 long years to catalog the entire Milky Way galaxy. Almost he has classified around 60,000 stars, and the original images, every stuff is here with our Kodaikanal Observatory. And the most prominent line or the most abundant gas in the solar atmosphere, it is nothing but hydrogen. We all know that. And the hydrogen have the spectrum like a Lyman, Balmer, bracket, series, fund, and all the stuff. And Lyman Balmer we can call that is 165, 62.8. That is the wavelength corresponding to that one. Very narrow band of the very narrow band filter we have to observe the sun at the hydrogen alpha wavelength. And this is a telescope, and this is one of the modern telescope we have here. And this is this mount is more like can be, as you know, that if you give the two coordinates like azimuth and elevation, automatically it will do the tracking. And we also have the auto guider for that, and we can see the lower chromosphere using this telescope. And very interestingly, this telescope is been operational from the year 2016 onwards, and we got a very good results from this telescope. And the basics behind that one, it is a CCD based, so you can zoom it to the very higher level, and we can find out the very fine structures in the lower chromosphere using this telescope. And earlier days, you may ask me what is the advantage over this one. Earlier days, maybe 3 photographs or 4 photographs used to people used to taken with glass plates, and nowadays we have all the stuff in the digital format. So as you know that digitally means we can do much more work, or the time cadence also, it can go in the orders of the few orders of the seconds we can go. Because it's a ground-based telescope, we can have a good time cadence, and primarily we can study about the lower chromosphere using this telescope. And this is a picture you can download, these images from our website. If you can visit www.iiapres.in, and every single day we used to take all that, we keep one good images in the website. If you wanted to take a sequence of the data, we can provide you for your research if you like. And these images you can also see some kind of the very, on the lower chromosphere, you can also see kind of the filaments and other structures. The filaments have been studied with Kodaikanal, other olden day data. Modern day data with hydrogen alpha, we can also study about the kinematics, the movements, the oscillations of the filaments, and the thread-like kind of the structures, the evolution of the coronal features. Everything can be seen or can be studied with this telescope. This is about simply the numbers, like how many data we have the year, and we have a catalog also. So if somebody is interested, they can use our catalog. You can use it, and we'll move on. I will just show you. Yes.
Can I interrupt you?
Always, you are most
we
welcome.
We will allow questions, okay?
Yes, yes, please.
Okay, so Gopal Chetty, you can unmute and ask.
Good evening, sir.
Yes, Gopal
sir, I
Chetty.
want to. Yes, sir. Sir, I want to ask about the resolution magnification power of the telescope, and I'm really curious if we can observe some galaxies clearly as well, near galaxies such as Andromeda with that.
I'm sorry, like this telescope is meant for solar purpose, and hydrogen alpha meant for all the filters we have put there, because the sun is so bright. Am I right? So we need to reduce the intensity. Like we have used neutral density filters to reduce the thing. We have compensated for that. So normally we won't disturb the telescope for stellar observations. And stellar observations means we need to give more integration. And there are many telescopes, as I already told you. You can visit our Kavalur telescope, and we have also Himalayan Chandra telescope. We have there, people are working with the galaxies and other stuff. Okay. Have I answered you, Gopal Shetty?
Yes, sir. Thank you so much. I thought that stellar viewing is also possible with this telescope. That's why I asked.
This is a very small telescope. That aperture size is only 12 centimeters. Very, very small. Because for sun it is sufficient. But if you wanted to go for a stellar observation, you need more light photons you need. So you can visit our Kavalur observatory. The primary mirror itself, the size is 4 tons. 2.34 meters. The size of the telescope size is huge in size. I think in a lecture, I think I not included anything about our Kavalur observatory. You can visit there also. Like in our website, there are many people in the audience. You can contact them. They can take you virtually to Kavalur observatory also. Kavalur observatory is a huge observatory. When we installed, that is one of the biggest telescope in entire Asia. So very nice telescope. You can observe that. Okay.
Okay. We'll take one more question.
Yes, sir.
Saurabh Bhattacharjee, please.
Yes, sir. I want to ask that how many ND stop filters are used in this kind of telescope to observe Sol?
I will take you to the specific your questions. I will answer little later because if I go to the f ratio and the diameter of the telescope and filters whatever you have used, it will be. Now, I just wanted to tell the story for a general public. Am I right? So I have a write up. You just send your email. I will send you all the details. I have produced. We have a good flyer is there. I will send it to you.
Okay, sir.
Like what are the specifications and what is the filter we are used and how the tracking system we are working. All the details, everything is with us. I will send it to you.
Okay, sir.
Okay, please move on.
Okay. This telescope this is also inbuilt telescope. Like we have, we have made this telescope, and state of the art, this telescope is, it will be rotating at the earth rotation speed. And we call this telescope as a white light active region monitor. You remember I was telling about the 6-inch telescope, that is a very small telescope. And we have a long observation from the year 1904, almost 100 plus years of observations we have. And this instrument will be complementing that one. So this is an amalgamation of both the old and the new. So the continuity we are doing with this digital as well as we are having with the photographic films also. But here we will be taking a tons of data. Like per day, if you are taking, if the sky is very good, we will be going approximately more than 1,300 frames or 1,500 frames we will take. But analog or a photographic film, we cannot do that much because it is very expensive. And this telescope, all these things are digitally stored, as I already told you. This telescope will be the primary mirror will be rotating according to the earth rotation, so that the images may not spear, or otherwise if you are not concentrating, or if you are not tracking properly, there will be a lot of disturbance will be there in your imaging. Okay, let me take you straight away to the back end. It will be, there's a concave lens is there that will be producing the parallel beam, and that parallel beam will go and hit on the beam splitter. 50% of the beam will be going to calcium K, and 50% of the light will be going to the G band. We call that as a G band. And these images I will just show you here, that we have a 2 CCD camera separately. It is mounted on a it is mounted on a optical table. Within the dark room we will be imaging all the stuff. The back end, when you see here, now you're seeing the 2 images simultaneously we are taking at the G band as well as calcium K. Calcium K is more like a proxy for studying about the magnetic field and other stuff. So you can very visibly, this is also chromospheric images. You can see about a beautifully sunspot. You can zoom it to very higher level to understand about the size of the sunspot, the leader sunspot, the lagging sunspot. One will be, it will be growing and it will be decaying. All these parameters with respect to time, you can measure with our facility. It will be very, very interesting. We have a long record for the sunspots from the olden days even to the present day. Okay, and you are seeing about almost approximately 2,500 frames or something we can do in the month of January. because the sky will be very, very clear. It's a winter sky, it will be very good. And as the days goes by, in the month of April, May, and all the stuff, the monsoon starts, we'll be getting very minimum sky. And in the month of November, December, then again it will be keep going high. We can, as I already told you, we can observe from the green G band as well as from the calcium K observation. Both the observations are synoptic observations, and any portions of the observations also you can zoom it and you can study it. So say for example, you are wanted to study about the very small spicule kind of the stuff, we can also do it. And you can, if you wanted to study about the sunspot in a great detail, you can zoom it, and we have algorithms written in the IDL and many other MATLAB and many other codes are there. Whichever language you are comfortable, even Python we are making coding now, and that's not a problem. If you have some science goals, you can use our data. Let me take you to the digitization. What is the digitization means? We have all the old data with us, and all the yes.
Sorry,
yes.
before you move to digitization, Deepak Pandey has an important question.
Okay, Deepak Pandey.
Deepak Pandey, please ask. Okay, he's not coming on. So, okay, his question is, do you make the telescopes or buy them?
Both. We can do both. In fact, some of the telescopes we have done it here, like the mirror and other stuff. Some of the things we also purchased. The H-alpha telescope, the tube and all other stuff, the drive and other stuff we purchased. Some of the material belong to us. Both. It is a some order. We can make it, and as well as we can do it. We have a good facility in our Bangalore office. We can do the optical shop is there, like optical laboratory is there. There they used to do the optical grinding and other stuff, and mirror coating also we can do it at Kavalur. So we don't have, in Kodaikanal, we don't have a mirror coating facility. We will send our mirrors to Kavalur, and they will do the mirror coating, like front silvered mirror we have. That can be, we will bring it back during the off season. Normally we used to do that.
Okay, thank you.
Okay,
please move on.
Let's come back to Kodaikanal Observatory. We have the digitization program, and as you all know that, I think you can see my image here. It's a picture of a solar eclipse. Can you see that one? I don't know. Any raised hands can answer it. If some people raise hands, then I can. Oh, okay, wonderful.
The picture I see is the digitization room. Somebody sitting there. That is the picture appears.
And and digital. Can you see my video? I am seeing.
No,
I am
there is no video coming.
No.
Okay, that video.
Video is coming. Just pin everyone.
AB video is there. In that one, you can see that one. Otherwise,
no, we can't see simultaneously two presentation. No, you have to show the video separately. I mean, if you stop sharing the slides and show the video.
Okay, I will try to do that.
How can we do we can't watch simultaneously.
Okay. Now I think you can see my video. Am I right? Can you see my video?
No, if not yet.
We can see your face.
Can you see my video now?
No, Ebi, I think as Rajaguru says, he had to.
No, sorry. What Ebi says is that his face. Yeah, we are seeing your face. Yeah,
you are seeing my face. Now you are seeing about the pictures. This is what I showed
you are just showing the pictures by hand. Okay.
Okay. This is a picture by the first day cover made by Government of India to commemorate the 100th year of discovery of the Evershed effect, John Evershed effect. And some pictures I showed you. This is about our digitization program. The 6-inch telescope we used to take the images. This all, I think you have missed it. And it is there in the photographic film, and now it has been digitized. Let me move on. Now you can see the picture.
we are doing the pole marking of this one, and simultaneously we are taken about the hydrogen alpha, calcium K, and white light. All these pictures have been taken, and now it has been very nicely. We have recorded all the stuff. It's been stored properly with a dehumidifier, which is otherwise the fungal attack will be there for all the photographic films. We have nicely we stored all the stuff. Okay, and there are many things like highlights of the results. I have just to put some few for you, like a heliospheric hemispheric asymmetry in the sunspot areas we can study. There are many people around the world, they are using our data. Latitude distribution of the sunspots and variations of the super granular parameters with the sunspot cycle, association of the plages with the sunspot sizes during the different sunspot cycles, the periodic and quasi-periodic variations of the calcium K. This all the stuff is related to sunspot and sun-related stuff. A very detailed way we can study using our Kodaikanal data. I think I missed or skipped many things. Like if you wanted to get a more detail, we have some experts here in our group. You can contact them. You may ask me what is the use of all the stuff, and we can predict or we can work on the nature of the sunspots and with the sunspot cycle, because during the every 11.2 years, sunspot will come, emerge, and the sunspot will disappear. And we call that as a sunspot minimum and maximum. The duration is approximately 11.2 years. It has been seen, the variations of the sunspot is seen in almost all wavelengths. You can take from the microwave, in the radio wave, and you can also take in the photospheric observations, many things. It has an influence. We can study about the sunspots and the nature of the sunspots and the inferior or superior sunspots, all the stuff we can study using our data. Okay, so I just put a plot about the studies what is being taken by our Deepankar Banerjee and his students. They studied about the different sizes of the sunspot. They studied using the white light images and calcium K images and H alpha images. It looked like a butterfly, am I right? And this is called a butterfly diagram. Most of the solar astronomers, they know about the sunspot thing. And this is one of the in worldwide, what is a scientific data which has been preserved for by the human race for a longer time is nothing but a sunspot. So we have the long record from the year 1750 till date. We have the record of our sunspots. This is you can see about the Carrington event and Quebec blackout and many other stuff. And there was some amount of minimum and all the stuff. It's all related to the sunspots. So in our data, with our Kodaikanal data, people are also working to study about the sunspot and sunspot area. Let me move on from the sunspot to, I will come back again to sunspot again and studies of the sunspot. And before that, I would like to show you some interesting observations happened in the Kodaikanal Observatory. And we have a huge record or huge collection on the record on the Halley's Comet. It appeared in the year 1906 or so. And I have the original record with me that when the Halley's Comet, when it came very closer to, I think okay. When you are seeing about the sunspot, when the Halley's Comet, when it was there very far away between the Jupiter and the Sun, Jupiter and the Saturn, you can see an image like this here. It is also recorded from Kodaikanal, and you can see the size is more like a single dot, and the tail is not grown, or you can see a small growth in the tail here. And comet size, as you all know, that one, the size is nothing but maybe 30 kilometers or so. And the sublimation is the process wherein which the rays from the sun will be ionizing all the material, and the tail will grow to the millions of kilometers. And some people during the 1986, when it appeared reappeared, people believe that one, the tail may also touch the earth also. So millions of kilometers the tail will grow. But the comet head, it is approximately the core of the comet. It's they call it a coma. It is approximately around 30 kilometers or so. They have a nice records of this Halley's comet, and it has been observed. The tail has been, they have the iron tail and the dust tail, all the stuff, it has been changed, and you are seeing all these pictures here. And even in this picture, what I showed in the picture here, you can see about there is a the tail is not uniform. The tail is split across. It has many components in that. It's these original records are in our Kodaikanal Observatory now. It has been sent to NASA Goddard Space Flight Center, and it is brought back here, and now we have digitized and we have kept here for further studies. If somebody is interested to study about the comets, I think they can contact us, our observatory people, or our scientific team. You can, if you contact, then we can supply the data to you. And Halley's comet appeared in the year 1986. And I'm just taking you to Kodaikanal Tunnel Telescope. It is being, we have a Professor Nagaraju here. Nagaraju is the primary person who is developing many instruments for Kodaikanal Tunnel Telescope. And this telescope, we can see very fine features in the sun, we can see it. And if I tell in the arc minute, arc second, I think, I don't know how much it will be, you can understand it. Maybe the seeing conditions in our Kodaikanal, it may appear up to 2 arc second to 3 arc second or 5 arc second. The sky will allow us to do the observations. And we can do the fantastic observations with spectropolarimetric observation like I, Q, U, and V. And you can contact Nagaraju here. He is in our group only now. And you can also, if you want to have any questions, you can ask him. Before, next I just wanted to just move on to tell something about Wilson-Bappu effect. The calcium K line is even regularly we are taking the observations here in Kodaikanal. The wavelength is 3933, and we can see that he observed that the calcium K observation in the cool stars among the strongest emission lines, which is originates from the star's chromosphere. He discovered that one, and along with Olin Wilson, that is the reason we call that is a Wilson-Bappu effect. They reported a remarkable correlation between the measured width of the calcium K emission line along with the visual magnitude of the star. The visual magnitude of star and the calcium K observations, he could find out a good correlation, and that is turned into, and they call it is called a Wilson-Bappu effect. Okay, and the Wilson-Bappu effect, it has been independently measured for many type of the stars, like O-type star, G-type stars, and you all know about the star classification. It has been Wilson-Bappu is also a founder of our institute, Indian Institute of Astrophysics. And before, let me take you to the library of our institute, and it's we have the good number of collections, very beautiful collections of books, not only in English, in many other languages, and astronomical languages of publications is being stored here. If somebody wanted to do any research, they can approach us and they can take the information from us. And you can see about we have unique collections of many data we have at the Kodaikanal Observatory, and the old hand-drawn charts is also now being digitized. And I just wanted to tell about this 18-inch telescope. The 18-inch telescope is being continuously used by Norman Foxen. This telescope is also in a good working condition. Earlier, they have used photographic films to do the observations. Now, for the sake of the nighttime observers, we have put an eyepiece and we can do the many other observations. Norman Foxen, he used almost for 30 years this telescope, and he classified approximately around 60,000 stars. And some of the records, all the stuff we have in our Kodaikanal library, we have some of the records. And let me take you to astronomy means time is very important. Am I right? Without time, we'll miss many things. And we need a precision also. And this is one of the oldest clock, and there is a good write-up about this clock by Rajesh Kochar, and it is being published. You can also see about it one. This clock, it is very, very old, and it's also in a very, very good condition. It is still working. And Madras and Kodaikanal observatories, it has been written, and it is published by Rajesh Kochar in the year 2002. Okay, in the Resonance Journal. And one more instrument we have, it's one of the oldest instrument. I took it from Kavalur Observatory. That is nothing but this instrument. At the back end, we have the prism kind of the stuff they have, and this is called, we call it is being used by Dalmier. So we call this the telescope itself Dalmier telescope. These two stuff will be moved to our Kodaikanal Museum shortly, and we have a good write-up. We can do that. And another telescope, the optics is not there, but this telescope dome is being renovated now, and we are planning to put a night sky observation with a DFM telescope. It is almost done, and if somebody said that they wanted to use they want to study about other stuff, and they can also digitally, the backend is, we have a good digital backup we have. So with the eyes, during the clear skies, we can use this observatory or a DFM telescope to do the night sky observations. And we have John Evershed, he stayed here in this, he did a lot of experiments here. That we called it a spectro telescope. Spectro. Within the spectro, we are seeing about those days they wanted to do the scanning. And because when you want to do the scanning, there is no electricity. So they invented a method to do the automatic scanning with a differential. When the sky condition is very good, the thick sky or a thin sky or a beautiful sky, they can integrate, they can change the integration time or exposure time. To do that kind of the stuff, they had a very nice mechanical setup, and with the oil seal, it is still in a very good working condition. So one can, all the images I think I have shown you here in my pictures. This 6 centimeter images of the hydrogen alpha images, or many other the outside of the sun, they can put an artificial occulter, then they can see the outer layer of the sun. That is called we can see about the prominence and other structures. That's all been done with this telescope, and it is still in a good working condition. Only problem is we don't have the sensitive films for that one. That 3933 calcium K, that particular wavelength sensitive films is no more available. So this instrument is no more, we are not using that. It's because of the lack of photographic films. But the instrument is in a good working condition. And let me move on to explain to you about the Kodaikanal Tunnel Telescope. This tunnel telescope has a 3-mirror system. The mirrors are almost 60 plus centimeters, 62 centimeters, big size mirrors. We have the 3-mirror system, and the back end we have the grating. That the grating can be tuned to particular, we can tilt it, or we have a motorized system to tune wherever we want. And we can study, presently we are using the calcium K wavelength 3933 to study about this telescope. I just took a picture from the back end. This is not a really good grating, because Nagaraj is here, he can tell more about our KTT. Nagaraj, can you speak one or two words? Yeah, can you please unmute and speak, Nagaraj?
Hi, about the tunnel telescope.
Yes, exactly.
Okay, hi. This is this is called the Silostat system, which is a light feeding system, which has, as you see, there are 2 mirrors. One tracks the sun and puts the beam on the second mirror, which is on the top, and that beam is vertically directed down into a tunnel. So there we have a lens which is 38 centimeter diameter. So I mean, this, like, you can take it as a telescope size. This is size-wise, this is the second largest telescope you can say in India, apart from, after multi-application solar telescope in Udaipur. It has equipped, as Ebenezer explained, it is equipped with high-resolution spectrograph. So we also carry out the spectropolarimetric observations. in various spectral lines to measure the magnetic field. So as you may know, it is the Zeeman effect that we observe. I mean, the Zeeman effect which splits the spectral line also introduces polarization in the spectral lines. So that's the basis we use for measuring the magnetic field. So mostly we do the magnetic field measurements in the sunspots. So is that okay, Ebenezer? Or
yeah, very good. Like we all know that was splitting of the spectral lines in the presence of the magnetic field. That is nothing but a Zeeman effect. So that's what Nagaraj was telling. And we can take a very narrow slit of light. We can allow that one to pass on. And if you keep that image on the sunspot, you can measure about the magnetic field of the sunspot. And it will be very interesting. Many students, Nagaraj used to guide many students also. So you can contact him. He is very much here with us, and you can take his contact number or so. And if you are so interested, you can come to Kodaikanal Observatory using. You can do the project here. And let me move on to the. There are many publications out there. That is, you can see in literature there about us. Let me take you to the radio astronomy. Radio astronomy is not new to Kodaikanal. And Kodaikanal, very long ago, Professor C.H. Shastri, he put a dish and he was observing, and they have published some nature papers also using Kodaikanal Observatory. Very recently, we saw the 8-element we combined in a Christmas tree fashion to make a broad beam. And the similar structures are available in Gauri-Bidanur Observatory. It is very near to Bangalore. You can also visit there. This the signals will be combined in phase. Meaning like each and every component need to be combined in phase, otherwise they will cancel each other, the signals. So the signals, we have a delay shifter and the kind of setup we have here that can be operated from the coronagraph. Olden days, we had a coronagraph in Kodaikanal Observatory, but it has been not in operation for more than 30-40 years or so. So we identified that place and we kept our radio instruments there, and we are getting a very fantastic results. And we can compare our results also with our other field stations at Gauri-Bidanur. And this is one of the, at 40 megahertz, you can see about the contribution from the thermal contribution from the sun. And let me tell you what is the thermal contribution from the sun. Okay. And this is another spectropolarimetry observations we are using at the radio wavelengths. And this is the level of the signals we are getting, very, very weak signals. You can imagine the signals, the radio signals we are getting from the sun is approximately 10 power minus 26 watts. 0.0000, you can add for such a long distance. 10 power minus 26 watts, we call that 1 Jansky. Jansky is a founder of, he's a man who discovered the radio emission from the galactic center and other things. And to honor him, radio astronomers, they call that unit, 10 power minus 26 watts, we call that 1 Jansky. So we can, and the radio astronomers, we use 10 power minus 4, 10 power 4 of Jansky, because sun is a very nearby star and it gives an enormous amount of the flux. Therefore, we call the solar astronomers, we call that as a solar flux unit. That is 10 power 4 Jansky. And we can see about the observations here. The observations, what I showed you, less than 100 megahertz, you can see it is approximately around 3 or 5 SFU. That much of signals can be very easily, we can detect it with this observation. You can see that one sun is rising and it is setting, and this is a transient instrument because it is fixed on a pole. We are not doing any tracking. Therefore, the beam will be, the sun will be drifting through that. Therefore, you are getting the peak around UT. It is approximately 5 or 30 minutes. You can see the maximum radiation. Then after that evening, it will be just going down. These observations, it is routinely done with Kodaikanal Solar Observatory. This data is available on the web also. So one can, if somebody interested to look into the radio astronomy part of the sun, they can use Kodaikanal, as well as we have Gauri-Bidanur Observatory and many other observatory. We have multi-frequency observation, we can do it. And here we are presently doing 35 megahertz to 85 megahertz we are doing. If wanted to, we are Gauri-Bidanur, we are building at a decimeter wavelength also. very high frequency also, 35 to 435 megahertz. Also, this instrument can work. So, if you wanted to use this data, it is available with us. And any other Newton Das wanted to ask some questions, I think. Newton, I think let me continue. And very recently, on May 22nd, this year, 22nd, we found emissions continuously coming from the sun for 6 minutes or so. Normally, radio bursts will be all type 3 bursts. It will be orders of less than few orders of the seconds. It will be type 2 radio bursts that will be. This is related to the coronal mass ejection. The enormous amount of the materials will be moved out from the sun atmosphere at the speed of, say, for example, 1,500 kilometers per second to even 2,500 kilometers. That much fast thing it will go. That will produce a wave that we call as a Langmuir wave. Langmuir wave, it's unstable. It will decay into electromagnetic wave. That can be detected with our radio telescope. So radio telescope, we have a radio spectrograph that can observe the full size of the full beam that we can observe the sun. We can identify the location using our heliograph. We have this suite of instruments we have. We have a radio heliograph, we have a radio spectrograph, and we have a radio polarimeter. Polarimeter can tell about, we can measure independently the I and Q, the Stokes parameter we can measure. We can identify the location where it is originating. We can use our heliograph. With kind of the spectrograph, we can identify the emission from the different layers of the sun, because the plasma frequency is directly related to the coronal density. The coronal density will be very, very strong in the lower part of the sun. Otherwise, the very chromosphere or photosphere of the sun, we have the density will be more. When you are moving out, the density will be decreasing. So the emission which is coming from these many layers, we can study about the propagation or the effects of the propagation, all the stuff we can study using the radio telescopes. Okay. And
maybe there is a question.
Yes, Prabha.
Sayandeep Nath, you can ask him.
Sir, can you tell us about solar wind that was observed a few days ago? How it was observed in Kodaikanal?
Kodaikanal, we cannot do the solar wind observations because solar wind is originating from the coronal poles or many other regions from the sun that go at the speed of 380 to 400 kilometers per second. That much it is going. It is continuously, it is constantly, it is going from the sun atmosphere. And you are asking about recent blackout days, and it has affected South America and North America. And at the very low frequencies, the attenuation level was too high. I have the record on that one. Unfortunately, it has happened on the night time of our Kodaikanal. So 14-hour duty, it has happened, but during that time, we are not observed anything. Otherwise, we can, the X-class flare and all the stuff, even we can go up to from few orders of the C-class flare and the M-class flare, we can study it here from Kodaikanal. And the Galvi, we have another field station. We have the dedicated solar observers are there. There we can measure about a very few orders of the B-class flare. Also, we can see it. Okay, that particular blockout, what you are telling, that has not been observed by us.
Okay. You can move on, AB.
Yes, okay. Like 21st June, we have observed a huge outburst, and we can also see that the outburst, it's a very strong outburst we have seen. And it's also normally type 3 bursts will be coming first. After that, the release of the type 2 bursts, type 3 bursts will be getting a type 2. But it's this unique observation we have seen from Kodaikanal. There you are seeing about the very slow drifting type 2 radio bus along with the other bus also we are seeing. We have a good places are there, and we have in Kodaikanal, we have a good outreach center we have, and we have modified, we renovated that one, and we have many facilities like old telescopes and all the write-ups we have kept here in our museum. and we have another good auditorium. We can conduct many classes and all. We, as already Professor Prabha said, we conduct a summer school and winter school at Kodaikanal. Normally 30 to 40 students we used to train them. We used to teach them for almost 2 to 3 weeks, and later timings they used to do the project here. And unfortunately, we could not conduct the summer school. And you are all here as a part of the summer school here. Okay, we have a lot of future challenges out there. And now we have put the digitization, and we have put a scanner here, the hand-drawn pictures from the year 1902 or from 1904. It's all available here. Now we are doing the digitization of the hand-drawn charts. That will, I believe, that will bring a lot of science to us. And these are the different varieties of the radio birds observed here at Kodaikanal. And we have many other plants, and we have nice features out there. And we can correlate with studies with other observations. We can do it. We are renovating all the old stuff, and we wanted to make use of. We wanted to bring new telescopes here, so we are working on that one. These are very old structures. I think maybe around 80 to 100 year old, I think, and it's in a good condition. So we are working on to develop this one. So thank you all. These are my Kodaikanal observatory staff. Our crew are there. So we are 60 plus people are here, and you can visit us at any time. Okay. Thank you.
Thank you, Abhi. That was a very nice tour of Kodaikanal Solar Observatory. So we have time for questions. If people have questions. Okay, I only see thank you, sir. Okay.
I presented very simple. Therefore, I think everyone could understand it. It's not no equations, nothing involved. So I think there's no questions.
Yeah, I hope you have inspired people to wish to come there and work on solar physics. Okay, somebody has a question. Satya, you can ask directly. Satya? Okay, Satya is asking when can someone visit? What is the procedure?
So now we have this pandemic situation. Otherwise, even anytime is fine here. And so far we are not open after pandemic. Anytime we can open. Already the government has given relaxation to open our astronomy observatories. So we have a good guest house here. So you can stay and you can do whatever you like here.
Okay, then there is Arvind has a question. Arvind, let's make it interactive. You can unmute and ask.
Yes, ma'am. So, in how much area is this observatory located? Like, how much area is in acres
okay,
or something?
the distance wise is very near. You know, it's a Madurai airport and Coimbatore airport. They both are nearby. Within 3 hours, you can reach here from the airport. And 100 plus kilometers is Madurai airport. And Rajguru can tell more details to you.
No, he's asking what is the total area of Kodaikanal Observatory?
Oh, area, it is, okay, we have 119 on papers, and we have part of the forest. It's a huge area. It covers almost 2-3 mountains are there here, up and down, and it's a huge area. Sorry.
Okay. So there are other questions which are like about the PhD program at IIA, which we can take up during the discussion session a little later. There is one question about fellowship internship programs at the observatory. I can answer this. Yes, we have fellowship and internship programs. Right now, things are not going smoothly because of the pandemic, but we will open it soon. Then Shribala has a question. She can unmute and ask. Shribala, you can ask.
And Rajaguru can tell about our visiting students program, VSP. I think Prava also can tell about it. We give the scholarship liberally for 5,000 rupees per month.
No, wait, hang on, Abby. We will do that announcement. That is a separate, yeah. So let's allow Shribala to ask you a question. Shribala, you can unmute and ask.
Good evening, sir. So I have having a doubt that we usually see the observatory's top is dome shaped. So is it just for allowing maximum night sky observation?
I'm sorry, your voice is not that much audible to me. And Prava, can you answer it?
No, I can ask the question for her. She says the top of the observatory is dome shaped. Is it for maximum night sky view?
Night sky observation we are not doing at Kodaikanal at all. So the dome structure is no, that is one of the. There are many structures to protect our telescope. So dome is one of that one. Nowadays, all the recent modern telescopes we don't have a dome kind of structure, and cost effectively we can move it and we can do the observation, and very easily also we can close it. We have the shutter kind of the stuff we have at the Kodaikanal. But olden telescopes, all the things we have domes.
Okay, so there are a few more questions which are quite relevant. I'm going to give Venugopal a chance to ask because Gopal Chetty has already asked. So, Venugopal, can you unmute and ask? Okay, so I don't know if it's on, so I will read out the question. Where do you save the data recorded every day, as the size of the data will be huge?
Yes, we store it in backup in drives, and we have the servers also here at Kodaikanal, and the users, they will be taking or downloading the data. If the volume is so much more, they will come here personally and they will take the data and they will take a backup from here. And we have collaborators, and the collaborators also they'll be also working with us, and we'll share the data with them. Now fast data transfer, the first level or second level data reduction is being done, and that's also been done by our people, and they can use it for the studies.
Okay, then let's take Gopal Chetty's question. Gopal Chetty, you can ask, and people like Rajguru can also answer this. Gopal Chetty.
Thank you for the chance, ma'am. But I guess my question was similar to the previous question answered. Like I was also asking that the data obtained from the observations, like which kind of instruments are you using, like supercomputers to analyze the data or some powerful softwares?
Computing facility, I think Rajaguru can answer it.
Yeah, Rajguru can answer.
Oh, so Gopal Chetty, the kind of data we obtain, it is not so huge. Okay, I mean, these days, the whole of 100 years of data is about 5 terabytes. So these days you can get a handheld hard disk with 5 terabytes. So, but for analyzing the data also, you don't need a big supercomputer for the kind of data which we produce at Kodaikanal. But in IIA we have a cluster. It is not a supercomputer. It's about a few hundred computing cores. I think about less than about 1,000 cores. If you know what a computing core is. A cluster is just like in your laptop, you have 4 cores or 6 cores. So like that, we buy computers like boxes and they parallelly connected. That is called a clustered computer. We have a IIA in Bangalore. We have a cluster which is about 800 cores, about 20 nodes, 20 boxes which are parallelly connected. It is not a supercomputer in the sense of what you have in the world as a supercomputer, but we don't need supercomputers for the kind of work done through the data at Kodaikanal. But there are other people at Bangalore who do big computations. For that, they need big computers. We normally go to CDAC or IIAC, Indian Institute of Science, has a big supercomputer. One can apply and use them, but we have to pay. All right, I think I hope I answered that.
Yeah, I think you did. So, okay, this is going to be the last question before we close the session. So, Aishwarya P. Anil, she, I believe. Oh, what happened?
Okay, just put if somebody has any questions, if they want to continue, they can ask the question later.
Yeah, so the last question is maybe Nagaraju and Rajguru can also answer. Is there a chance of errors in data that is collected? If so, how do we detect it?
Oh, I don't know. Nagaraju, you want to take it up? I don't know what is the meaning of errors when you make an observation, when you take a record of number of photons collected, there will be some noise. If you want to call that as error, yes, they are there. Any observation will have some noise and error. They are detected by analysis. You do a data analysis, and as a function of time, you see how many photons are for a particular source, which you expect to be nearly constant. If it is varying, then that means there is some noise in the data. There are very different ways of analyzing noise in the data. Error means, suppose if you make a mistake while observing, if there is a sudden disappearance of thing, those kind of errors you can easily detect. I think I don't know if anybody taught you about data analysis as such,
No,
noise and errors,
no, that's
and
not covered. Yeah.
not covered. But anyway, if your question is on that, let's hope that
I
we
think
teach you next time.
Rajguru make it clear that mistake is not the error that we consider here. So what he mean to say that if there is a mistake by the observer, so that is not the error. By error, we means the contamination of various sources to the observational data. Now we know that what should be this contamination, and we reduce those data in such a way that that contamination or the error is removed. But still there are some error which cannot be removed, and that's why the observational data has an error bar. So we make that this is from plus minus some range.
Yeah, I don't know what he really meant. Maybe Aishwarya, you can unmute.
Yeah, I think it's okay. I mean, that requires more discussion. Let's close the session.
Okay,
Okay,
the errors can be, Prabha, let me tell only two, 3 words. The error may be there in the observation timings. Like that error can be, we can simultaneously from other observatories, we can synchronize the time, and that error can be reduced. And the recording from the CCD cameras, that will be some of the pixels may be faulty, that they do the calibration, and they will identify which portion of the CCD is wrong or which pixel is wrong. So they will do the pixel corrections is there. So apart from that, there are some human errors also may be there. So the errors.
Yeah, so there are different kinds of error, and one has to know what one is talking about. So that is required to answer this question. Okay, so I would like to close the session. Thank you, Abhi, for a wonderful tour of Kodaikanal. So the summer school is now officially ended, and people who would like to interact with the different lecturers, they can stay on, and the ones who would like to log out can do so. So let's take just 1 or 2 minutes break, and then we'll commence. We'll start with the question answer session. Let me see how many people remain. So we need to
There is a flood of thanksgiving going on.
Thanksgiving?
See the chat box.
Oh, yeah. Okay, looks like many of the participants wish to stay on. All right, so I think the Thanksgiving is over. So let us start with the next session, question answer. So I hope all the lecturers who committed are here. It's hard for me to see names. Okay, I hope they are there.
I'm here,
So,
Rajguru. I
you
gave
are there.
lectures. I
Yeah, I'm
lectured.
here too. Prava,
Okay,
Moshimi.
thanks. Uh,
Yeah,
I
Prava,
guess.
I'm also here. Piyali.
Okay, good.
Vivek is here.
What about
Vivek.
YouTube?
Sorry?
What about YouTube? Let it continue or shall I stop?
If there are people watching, I think it's okay. You can continue. Yeah. Is Sayori around? If we can take questions from YouTube also, it may be, maybe not. Okay. All right. So let's start the.
Jayant is there?
Yeah, I'm here.
Okay. Nice to see you.
So I just want to define some way in which people can question so that I know which question to direct to which person. So to the participants, when you are typing your question, please type, maybe you can type the name of the lecturer from whom you want the answer, or you can type sun, solar physics, or stars, or galaxies, or cosmology, so that I can direct it to the correct person to answer. Okay, so we can start. Okay, so people have to type in your questions and please start. Okay, so the first question here. So there are several general questions about PhD at IIA. I think we will leave that for the later when we are closing, and we'll deal with the science questions. So the first question is from Tamiz Malar. She can unmute and ask to exoplanet. So Susan.
Hello, sir.
Yes.
I have a couple of questions regarding exoplanets. So I recently read an article about a gas giant with a carbon isotope, which is really very far away from its star, hot star. So how those kind of planets are, they said the presence of elements determines the way in which the planet and the star is formed and the condition in which they are formed. So how is that determined, and how planets so far away or so close to the star are directly matched?
Okay, so your question is that how the planets far away from their star are formed, right? Or how they are detected? What do you?
I want to ask the kind of elements present in the planet. How does that tell us anything about how that planet is formed?
Okay, fine. Good question. So what happened here, you know that how a star forms. The star forms out of the collapse of a huge cloud made of hydrogen and helium mainly. And so because of some perturbation, they start collapsing due to their own gravity. And then the protostar, that is the center becomes so hot that it starts nuclear burning. Now, in that way, the star is formed. So once the star is formed, there are some leftover gases and dust. They form a protoplanetary disk around the star. So that's just like a donut type of thing. So it's a disk type of thing. And in that disk, first magnetically, the dust particle, they collapses and then they grow up. But before that, the gas collapses in the protoplanetary medium, and that gives rise to giant gas planet like Jupiter, Saturn, and all those things. So once this gas planet formation is over, then this dust particles, they coalesces with electromagnetic field, and then when they grow up sufficiently large with their high gravitation, then they again accrete matter from by their self-gravitation, and these rocky planets are formed. Now, what we find that in our solar system, the gas giant Jupiter is far away from the sun. But in most of the stellar system, the planetary system that is discovered, there the Jupiter size of giant planets are very near. So why this difference, that is resolved by a theory that is called migration. So what happened, our Jupiter, all the giant planets are formed much away from their star. But because at that time in the protoplanetary disk, due to viscosity, they start traveling towards the star. Now, for all other systems that we have discovered, this giant planet, they travel and they migrated very near to the star. But for Jupiter cases, what you are seeing that Jupiter, the place where Jupiter is now located, it was actually born much nearer, and then it started migrating, spiraling due to viscosity, and started approaching the sun. But at that time, Saturn was born. So the Saturn pulled the Jupiter back far away from that. And so the migration could not be completed in the solar system. So the larger is the protoplanetary disk, you can see the planets far away from their star. So, and it depends on what is the brightness of the star. Suppose the star is very bright. Okay, then what will be happen? Because of its radiation, this protoplanetary disk will be evaporated completely and no planet will be formed. So up to, the spectral type F, O, K, M, like that. So in the F star, we get very few number of planets, but most of the planet we get it in M type of stars, and most of the rocky planets are also around the M type of stars, whereas the gaseous planet and the rocky planets are around the solar type of stars, or even with F and other spectral types. So in that way, the planets are formed nearby or in the far away from that, depending on the width of the protoplanetary disk.
Okay, next question is Sugyan Parida on stars. Ken can take it.
Ma'am, I want to ask, what are primordial stars, and have we detected any such stars?
Maybe Jane can take it. This is for the first.
So primordial stars would be the stars formed right out of the Big Bang. And very hard to detect because it's so far near the beginning of the universe. I think every now and then you hear someone say, okay, maybe we discovered it. But I don't think there's any firm evidence so far. Right, Prabha?
Yeah, that's right. Okay, so next question is neutrino cosmology. So Subinoy. Akash, you can ask your question. He can also ask a question. Akash, are you there? Okay, he's not able to ask. So the question is, what is neutrino cosmology?
So we know that neutrino has mass from solar oscillations and atmospheric oscillations, but we don't know what it is. And today, the neutrino density in the cosmos is very much lower compared to dark matter, dark energy, or baryon. But in early time, in radiation-dominated era, neutrino was carrying almost 3/4 of the energy density of the cosmos, and universe was so dense that though they are very weakly interacting, that time that interaction can have effect on the CMB, cosmic microwave background. So studying the cosmic microwave background, you can constrain the fundamental property of neutrino. And Big Bang nucleosynthesis, that is neutrino cosmology, which is unknown yet.
Okay, next question is from Moshmi. So Omkar has a question. Omkar?
Okay, ma'am. Hello, ma'am.
Hello, yeah.
On that your lecture day, ma'am, you told how we count the number of stars in a galaxy. So, ma'am, how do we know the number of galaxies in the universe? Just like I read somewhere there are 2 raised to 10 raised to 11 galaxies in the universe. So how do we know that number, sir, ma'am?
I'm not sure that we know that number very accurately. So a lot of the evolution of the universe at higher redshifts is still unknown to us. We can estimate the number of galaxies in nearby galaxy clusters in our nearby local universe, but to go to higher redshifts, it becomes a lot of errors creep in. So I don't think we can really estimate the number of galaxies in our universe. That is not possible, I think. Maybe you can estimate the number of stars in a galaxy approximately using the luminosity, as I mentioned, but estimating the number of stars is galaxies in the universe is a much more difficult problem. Okay.
Yeah. If I want, again, I want to add, first you have to define in what region. We don't even know whether universe is infinite or compact. So
yeah.
Okay, so let's move on to the next question. People are typing fast, so I am unable to. Yeah, I'll take the question, I think, for Jayant. There are many cosmology questions, but they are repeated. So, okay, first we'll take Sujan's question for Sujan. So, Shobhapati Krishnan, please unmute and ask. We'll come back to the cosmology questions later. Shobhapati. Okay, so, yes.
Am I
Yeah,
audible?
Yes.
My question is to Sujan sir. Sir, could you please shed some information regarding exomoon and its detection and the existence of exomoon? Like how we detect the exomoon, like using the same transit method, like how we detect exoplanet. Like that, can we use the same transit method to detect exomoon?
Yeah. So let me first start with the end of the question. So far, we have not yet detected a single exomoon. The competition, the fight going on, the struggle, who will discover first the first exomoon. And that is because the size of the moon will be very small compared to the planet. Now we know in the solar system, most of the planets, except Mercury and Venus, all the planets have moon. And now this moon varies in size also. In different moon has different size. Like our moon is fifth in size, and the biggest satellite is Ganymede, which is orbiting around Jupiter. And the ratio between Ganymede and Jupiter is quite small compared to what is the ratio between the moon and the earth. Now these moons have been formed in different way, not like the planet was formed. The moons around Jupiter, Saturn, of these gas planets, they were formed similar to the scale down planet formation, that after the planet is formed, whatever leftover dust was there, that has made these planets, the satellites, and that's why the gaseous planets have several 70, 60, even 100 of moons, but Earth moon has been formed in a different way, probably by the collision of a big object. It was named Theia. Now, if there is a Jupiter type of planet, very big planet, and which has a satellite, that can be detected by the time delay in the transit light curve. But the problem is there, if this planet, this Jupiter-sized planet, is very near to its star, then this, because of the immense gravitational field of the star, this satellite or the exo moon may be detached and it may go and jump over the star. So therefore, it is very unlikely that it might have formed. The exo moon was there with the giant planet, but when it migrated towards the star, this exo moon has been destroyed, or it has been detached and jumped to the star. But still, there are some way of finding out. One is there, that when a giant planet transit the star, then in the transit light curve there will be some notch, because of the moon may also transit if the alignment is proper. Now, on that aspect, I have suggested, along with my collaborator Mark Marley of AIMS NASA, that the polarization may also work as a potential method to detect exomoon. So, for example, there are some kind of planets which are visible, which are far away from their stars, but they are quite young, and that's why they can be imaged directly. Now, if a moon transit this planet, then the polarization will be non-zero, and in the polarization signature of these planets, the signature of the moon will be prominent. So this has also been proposed. So both the methods are being tried to detect exomoon, but so far no exomoon has been confirmed or detected. Sometimes there are news that exomoon has been detected, but those are still false alarm. So because it is extremely difficult to detect, and radial velocity cannot detect exomoon, only the transit method, that is in the TTD, that is the transit time variation or transit time delay, can tell the signature of exomoon, or polarization from the system of the star and the planet can tell about the presence of a exomoon. So I think the next generation telescope may be able to do such type of thing, and we hope that in near future we can detect exomoon.
Okay,
Thank
so
you, sir.
next question is to Jayant. So Saurabh Bhattacharjee, you can ask. After that, we will take the solar physics question.
Sir, I want to ask that can you tell us more about dark nebulae, the interstellar clouds, and it's about its darkness?
Right, so there's many different types of interstellar clouds. You get the very light, very small clouds, where there's not very much matter at all. Some of these may not be gravitationally constrained, so they're just they'll just break up. And then you start getting the denser and denser clouds, and you get clouds of different sizes. So the dark, you will get small dark clouds, which are very dense. And you see them because they block the light from more distant stars. So what is doing the blocking is the dust. As I told you in my class, the gas will block in specific lines. The dust will be a continuum blocking. So it'll block the light from any distant stars. So the way you detect them is that you look in a star field, and you'll see them as a black patch against the stars. If you remember the extinction curve, the longer wavelengths are less extincted. They're absorbed less, and so you can go and you can look in the infrared, and you can map these clouds by looking at the stars that appear. And then you go all the way to the very densest clouds, these giant molecular clouds, like the Eagle Nebula. And this is where stars are formed. So interstellar clouds of all different sizes and densities, from very thin ones that are very difficult to detect to the very dense ones, which can be self-gravitating. Okay.
Okay. So next question is Vivek Gusain, and he has a solar physics question. So either Rajguru or Piali can take it. Vivek, can you ask your question? Okay, I think he's not on. So I'll read out the question. His mic is not working, so I will read out the question. Why sun's magnetic field reverses its polarity, and why it is not in the same direction all the time? Who will take, Rajguru or Piali?
Okay. Yeah, I can start. Probably Piali can. So the sun's. Let me share one picture. Let me see if I can. Okay. Anyway, so as you might have heard in our lectures, when the sunspot appears in the northern hemisphere, there is something called a Hale's polarity law. So there are usually sunspots appear in bipolar configuration, there is a one sunspot of one polarity and opposite polarity of the following sunspot. As the solar cycle progresses, the following polarity magnetic field slowly gets advected to the pole. And so the following polarity eventually replaces the polar field. So that the reverse of that happens in the southern hemisphere. So this repeats every 11 years. So this is what we observe. So there is, your question is why this happens. There are attempts using certain models of dynamo, how the solar interior operates a dynamo, and there are certain surface processes. What I just explained is what is happening at the surface, and it couples to a dynamo which is operating in the deeper layer. And but the dynamo is not fully understood. So the actual answer to your question, why this happens, is not fully understood, but we very well measured this. There are some phenomenological models, but maybe Piali can answer that in detail.
Not so much in detail, but if it is allowed, maybe I can show a movie. Oh,
I think the screen sharing is stopped. Screen sharing is not allowed, looks like.
Oh, okay. Oh, wait.
If you can allow the screen sharing, yeah.
I am co-host. So, Crispin, can you make her co-host? That would be nice.
Okay.
Maybe you can make all the lecturers co-host, and then you can assign the host to me. Yeah, I think I can now share. Yeah. So I'll just share my. Please make Rishabh the host. Now I think you should be able to see my screen, right? Yes. So yeah, this is a very popular movie. So which Rajguru would also probably have. So this.
Yeah, I also have that. Showed it. Yeah. Go ahead.
Yeah. This basically shows this Babcock-Clayton effect, or how sunspots decay and give rise to this large-scale fields. If I run this movie, so you can see. See, this is the sun, and on the face of the sun, you see lots of sunspots. And the yellow and the blue are basically the radial magnetic field of two different polarities. And then they basically emerge and then decay. So this whole thing, now they have basically opened up the sun, and now you can see the timeline at the bottom, and you see that these sunspots are decaying, and then they are giving rise to this really weak poloidal or the dipolar magnetic field of the sun. So essentially what is happening, most people believe is happening, is in this other movie here. So if I run this, so this is again the entire sun, you see the surface. So there are these sunspots appearing and disappearing, and now you look at a cross section of the sun. So the center, the bright thing in the center is the core, and then you have these magnetic field lines in gold, right? So because of the differential rotation, I think Rajguru must have spoken at length about differential rotation and what is known as the alpha effect. So basically these magnetic field lines become wound up, and then they give rise to these different components. One is the sunspot field, and the other is this dipolar field. So you can see that that some of these field lines are coming out of the poles and then entering here. Those are the dipolar fields, whereas these are the fields, the toroidal fields are those which give rise to the sunspots. So essentially there is a lot of dynamics which is going on when the magnetic field is interacting with the solar convection, as well as the rotation and the what is known as the meridional circulation. So all these flows in the interior of the sun are interacting with the magnetic field, and they give rise to this kind of a solar dynamo, which makes the magnetic cycle go on. The magnetic cycle has a time period of 22 years. So as you know, so it's not that, I mean, all these planets and stars, I mean, they can have magnetic fields. I mean, as you know, the Earth also has a geodynamo, and sometimes the polarities flip, but that dynamo is very different from what we have in the sun. So in the sun, it is more or less understood better than what we understand in the geodynamo. So yeah, this is what I wanted to say. So I don't know if it answers the question or not, but yeah, let me unshare the.
Okay.
Yeah.
Really, the polarity of Earth magnetic field also changes.
Yes, that is what I said. It also changes, but it is not as periodic as 22-year. It is not. It is
No,
more
it's
chaotic
a very
than.
long period. It takes million years to change.
Yes, yes, but it is not. It is not periodic. It is more chaotic than the solar dynamo.
Right.
The regularity is not as much as the solar dynamo. Even though it may be longer scale, but still it is not. I mean, from the simulations, not from observations. I'm talking about geodynamic simulations.
Okay, thanks, Piali and Rajguru. So there are many cosmology questions. Okay, so I am going to filter them because there are just too many. So next question, Samantha Rath can ask the next question. Samantha?
Yeah, am I audible?
Yes.
Yeah, I wanted to ask that since now we are in the dark matter dominated regime, and we discussed today that in the matter dominated regime only galaxies form. So, till what amount of time period in the future would we be able to detect galaxy formations? And also, are we going to detect any kind of structural formations in the dark matter dominated era?
Okay, so first to clarify that we are not in dark matter dominated era now. We are in dark energy dominated era. A few billion years back, dark energy domination has started. But universe has spent almost like 7 to 8 billion years in matter dominated era. And in that era, the galaxy has started form and many galaxy cluster has formed. Once you decouple from Hubble flow, means once gravity wins over expansion, then you are not affected. Then that's why still the which has decoupled from Hubble flow, still the galaxy formation, star formation goes on. But now in dark energy domination era, suppose from large distance he wants to cluster, bring matter together, it's not possible because dark energy is a very large distance phenomenon. So in small scale, you can still produce because matter has already clumped together and it has, because in small scale you don't see the effect of expansion. So that's to answer your question. But as we wait more and more, and as we showed in the movie, the dark energy will take over more and more, and then it will be very hard to form new galaxy even in smaller scale. It's a few billion years from now.
Okay, thanks. So next question we'll take, okay, Tamiz has already asked, but okay, I think it's okay to give her another chance. So she can ask to Susan, exoplanet. After that, we'll take question for Jayant, I think. Tamiz?
It's Tamil Malar.
Oh, sorry.
Hi, sir. Hi,
Tamil,
sir.
yeah.
So I read about the direct imaging of exoplanets being so difficult because they are either so close to their stars or too far away. So what are the challenges other than the star's brightness obstructing direct imaging?
So far, see, the thing is that the planets are sufficiently bright for getting the observation even in the near infrared. One challenge is the distance. If the star is say 3000 light years away, then you get very less amount of light from the star itself. So forget about the planetary light, because the ratio between typically the ratio between a close-in giant planet radio flux and the star flux is about 10 to the power minus 5. So if you consider the ratio between Earth light, reflected light, and the sun's light, the ratio will be 10 to the power minus 8. So imagine the flux of the sun is 10 to the power 8 times larger than the Earth. But we can block the star by using coronagraph. However, there is a limit to that. We cannot If it is very near, we cannot block whatever be the big the telescope. So the resolution is a problematic thing. If the planet is very near to the star, we cannot resolve whatever big be the telescope, even if it is 100 meters, we cannot resolve the planet from the star. If it is away from the sufficiently away from the star, then we can block the starlight and we can image it. Like I have shown you that directly self-luminous planet or directly image planet, how they are photographed in infrared. So in that way, it could be done. In fact, we expect that this James Webb Space Telescope will image several such type of planet by blocking it. And then there is a Gemini telescope already operated. They have this, and the Keck telescope also, they have this facility. So the thing is that you need to fit a additional instrument called coronagraph with your telescope to block the starlight and you can image it. So this is till now this is a challenging thing, but with the improvement in the technology, this challenge will be circumstances. But I think the main interest is to resolve the Earth-like planet. So that can be resolved because they are far away. At least for solar type of star, they are 1 AU, that is 1 astronomical unit. They can be resolved by a telescope. And if the telescope is very powerful, the starlight can be blocked. But if there is a habitable planet in an M dwarf type of thing, their habitable zone is so near. There is an Earth-like planet around a M dwarf star such as Proxima Centauri, Trappist. They cannot be resolved by any type of telescope.
Okay, thanks, Sujan. So next question, I'm going to allow Vishwanath Mahapatra to ask. He has a question for Jayant about his
Yes,
books.
ma'am. Am I audible?
Yes.
Am I audible?
Yes, you are.
Okay. So my question is directed towards Professor Jayant Murthy. And my question is, I want to have some book recommendations because I can see his library looks very rich. And what are your favorite books, sir? If you can tell us.
Could you just say one more time?
Okay,
Repeat the
so,
question.
sir,
Jayant,
I
he's
want
seeing
to.
a lot of books behind you.
Yeah, there are a lot of
I
books
wish to
behind me.
have,
Yes.
I wish to have some book recommendations from you, sir.
Oh, okay. Book
And
recommendations for what?
and
For
what is your favorite book?
for what? Fiction, non-fiction,
Non-fiction, of course.
non-fiction. Well,
Because we don't want to become astrologers.
the books that I really liked, and these are old books, is Asimov's. What was it called? I'll bring it in just a second. But he's got a 2-volume set of an introduction to all the sciences. And this I read in the 70s. So that's what, almost 50 years ago, but still very relevant. And then other books that I like are Simon Singh. He's written a few books on Fermat's theorem. He's written a book on the Big Bang theory. He's got that great insult from what's his name? This cosmologist, the Dutch cosmologist. Anyway, said the guy's a pain from any angle, a spherical. He's a spherical pain. So those are my favorites. Stephen. I mean, this guy Simon Singh is an excellent writer. So for a more recent one, I would get him. But if you can go back to Asimov's books, those are very, very well written and still quite informative.
Okay, shall I move on, Jayant?
Yeah, sure.
Okay, so so I think I'll take okay, we come to cosmology question after we first take. There is a general question which I think any one of you can answer from, what is his name? Oh, Prasad Rathore. Can you unmute yourself and ask? Are you there? Okay, maybe he's not there, so we'll come back to him. So we'll take a cosmology question then. Now, next. I have to filter. There are many general type questions. So
There is one by Bharat Kumar Kannan that looks, you can ask her.
yeah, let me do the reading.
Shall I read that?
No, we'll allow him to ask. So Bharat Kumar, are you there? You can unmute and ask.
Yes, ma'am. Good evening, professors. So, my question is that why is that the Big Bang theory the Big Bang theory triumphs over the other theories regarding the formation of universe, or is there any possible explanation that sidelines the Big Bang theory at least in one way or the other?
Okay, so I think here is a misunderstanding many people have about Big Bang theory. When in cosmology we say that we had a hot Big Bang, it does not talk about the cause or the origin of universe or at t equals to 0, because that is singularity. Or hot Big Bang means all we know and all we mean is that we started with a very hot plasma, and that has been experimentally verified. So it is not a like an assumption or anything. We know that hot Big Bang was the case, and CMB is a proof for that. Big Bang nucleosynthesis is a proof for that. Now, what caused that Big Bang? That is a unknown thing. That how space-time emerged, or there exists another sort of like eternal space, that is related to inflation and how inflation was caused. So Stephen Hawking has some direction, but it is still unsolved. So in there are many other theories which you can think of, and still people are working on it. In physics, we don't speculate. If observation can detect it, detect it. If not, then we have to leave that.
Well, the famous alternative to Big Bang is the steady state, and that has been ruled out by observation. The CMB rules it out. Okay, so next question is Vishnu Bharati. You can ask. This is dust. After that, there is a star question. Yeah. Dust. So, Jayant, I guess. Vishnu Bharati, are you there?
Yes, ma'am. Yes, ma'am. Yes, ma'am. Present, ma'am. Good evening, ma'am. Thanks for giving me this opportunity, ma'am. I have one doubt, ma'am. How to detect cosmic dust in space, or which is the best method used to detect the cosmic dust? Sir? Could you please explain this?
All right, so you're talking about interstellar dust within our galaxy. You can also detect it in other galaxies, but let's focus on our galaxy. So there's the two ways to detect it. One is in an absorption. As the previous question, it blocks the light from more distant stars. The other way that's becoming very important now is to see it in emission. So if you look, the dust is heated by stars, and so it's heated to a temperature of anywhere from 20 degrees Kelvin to maybe 25, let's say 10 to 25 degrees Kelvin. And so it'll emit in the infrared. So the first evidence that there was dust clouds everywhere came from IRAS, the infrared astronomy satellite. And now with missions like Planck, Herschel, Planck, and so on, these are cosmology missions, but they can't do the cosmology without understanding the emission from our own galaxy. And so they have to subtract the foreground, which is dust emission. So they have made excellent observations of the dust within our galaxy in the infrared. And what they do is they see what is essentially the black body emission from the dust in the infrared. So you can look up the Planck papers, and they have some very nice maps of the dust emission in our galaxy.
Yeah. Okay. Thanks, Jane. Next question is Ashmita, rocky planets. So, I guess Susan. Ashmita, you can unmute and ask.
Good evening. Am I audible?
Yes.
My question is from Sujan sir. Why are the rocky planets closer to the sun? Like, why is our solar system an exception in this case? If we look at planetary system formation, sun was formed, then it's logical to assume that more gas must have accumulated around that region. Then why rocky planets were the result?
That is because of the gravitational field of this dust and the gas. So the gas was moved by the stellar radiation. So the gas was concentrated far away from the star, and they accumulated to become the star. Actually, what happened that during this photostellar region, other thing that the star was forming and it was emitting huge amount of energy, and so the protoplanetary disk was some sort of dispersing, and so the gas was far away. If the gas was very near, it could have been accreted to the star itself, and it could have fallen into the star, and therefore only those gases which were far away from the star, they condensed under their own self gravity and formed the planets. That's why. But then once it was formed, then the dust was there. Dust was quite nearer because of their gravitational self gravitational field. But it is not that true that the dust is only in the nearby. We have a Kuiper belt where there are a lot of ice and dust particle like Pluto and Eris and Haumau, and there are many rocky objects in the Kuiper belt. Even beyond the Kuiper belt, also we have discovered some of the rocky planets there. So it is not true. The leftover dust and the ice was there in the Kuiper belt, but because the density at that region was so low, there the particle was so far away that they could not coalesce, they did not collapse to form planets. But the dust and gas was there all over the protoplanetary disk.
Okay, thanks, Sujan. Next is Gopal Chetty, Subinoy. Gopal Chetty. Okay, I cannot, he is not there. So then we'll move on to next question. There are many cosmology. So there's a star question from Tamil again. So can you ask Tamil?
Hello, sir.
Yeah.
So
You can tell who you want to answer from.
I would like to ask Mr. Jayant Murthy, sir.
Okay, go on.
So, in star clusters, since the stars are usually much closer than they are anywhere else, why didn't, and since they also form in the same time period, why didn't they become giant stars instead of becoming cluster of smaller stars and end up exhausting their fuel easily? Is there any principle behind it or any consequence of action for this kind of behavior?
Who was this question to? For me, was it?
Yeah.
Yes, sir.
Yeah.
Yeah. Okay. So for when you're looking at star clusters, they look small, or they look close together when you see them from us, but the stars are really not all that close together. There's still a light year, maybe more, between the stars. I mean, I really don't know the number, but they're not that close. They're still independent, and so what happens is that when you get a star forming, it's not that large scale a phenomenon. The entire solar system is only a few hundred AU in size. So this is something that's always true in space. Things are always bigger than you think, and things are always less dense than you think. So if even in a star cluster, the stars are just not close enough for you to get all these stars to get one giant star. There's other things that go along too. Now the cooling in stars is fast enough that the stars contract fast. So you don't need as much mass to form a star when you're forming it. The reason you get so many stars in a cluster is because the shock waves from one star forming seed the formation of other stars. So there's many different things going on there. But basically, the answer to your question is that the stars are really not all that close together. So that's why you don't get a giant star.
Okay, so next we'll take question for Moshmi from Sri Bala. Sri Bala, are you there?
Hello, ma'am. Am I audible?
Yeah. Hi. Yeah.
Okay. Good evening, ma'am. Ma'am, I just wanted to ask. So, while forming, how is irregular galaxies formed? Is it from the merging of two spiral or elliptical galaxies or something?
So no, I think when you merge ellipticals or elliptical and a spiral, usually you'll end up with a larger elliptical or sometimes a larger spiral. So it's thought that the regular galaxies are formed in the process of galaxy formation itself, but I think they did not have enough mass to really form a rotating disk or enough mass to form a nice ellipsoidal structure, because most of the irregular galaxies that we find, that we observe, are low in mass. Since they are low in mass, it's thought that their potential, their dark matter potential, is also pretty shallow, and that's why they haven't formed a nice rotating disk. I think another way in which irregular galaxies are formed is through the tidal tails. So we know that when galaxies interact with each other, due to tidal interactions, you can form galaxies in the tidal tails. So some irregular galaxies may have formed like that as well. So I think these are the two main scenarios.
Thank you.
But historically,
Yeah.
they did think that galaxies did form by the mergers.
Huh.
So it's actually a good question.
It's a
only
good
50
question,
years
but
ago.
yeah, but when you form galaxies through mergers, especially in simulations, usually you don't form an irregular structure. Either you form an ellipsoidal structure, it settles into an ellipse, or if the mass ratio is small, it can still remain as a spiral galaxy. That's what you see in simulations, at least.
Okay, so...
But it was a good question, yes.
Okay, so we move on to one cosmology question, and unfortunately, I think we will not have time for more. After the cosmology question, we'll take some general questions which students may find interesting, a couple of questions, and then we'll close the session. So Gopal Chetty, you can go ahead and ask your question.
Thank you, ma'am. My question is, sir, like your viewpoint regarding this, as I'm always fascinated towards the unsolved mysteries in physics and cosmology. So I wanted to ask you if you can provide an explanation towards the fine-tuning problem as well as the baryon asymmetry. Like, why did matter tend to have an upper edge over antimatter while the formation of the universe?
Okay, so there are two questions you asked. One is fine tuning, that I have explained about the cosmological constant in detail in the lecture. But I'll take the next one, baryon matter antimatter asymmetry. So here also I think there was a discussion in another lecture. So main thing is from inflation, we talked today that if it is a neutral field, that I did not talk. So number of matter and antimatter has to be same, because from inflation, all the matters appeared in the universe, all the known matter. And then what happened that somehow the antimatter has vanished. And now this process is called baryogenesis. So there are some conditions needed to produce that. They are called Sakharov condition. You can search, but to satisfy all three Sakharov conditions to have baryogenesis or matter antimatter asymmetry is very hard. So within our known particle physics of standard model, it is not possible to have. matter-antimatter asymmetry. So you need some new physics, perhaps phase transition or some new idea which is unknown. And so that's itself is an open area of physics research. But there have been some paper, but till now, the proof of that is not there. But one promising area is gravitational wave, because of some strong phase transition, matter asymmetry was created, and that will create gravity wave, and LISA can detect that. It has a very specific frequency range. So that's it, but it's an open question that why matter and why the antimatter has gone. Please.
All right. So there are many good questions actually in cosmology, but unfortunately we don't have time. So please write to Subinoy if you want to get more answers. So there are, I'm going to move on to some general questions. So like Adarsh Kumar Gupta, you can ask your question, because this everybody can chip in.
And my question is, what is the role of data scientist at IIA? Like I am a beginner and I am learning machine learning and data scientist. So how can I use my skills to explore the universe and especially for the IIA? Yes, sir.
Okay, who will take that question?
Yeah, I can do that. So data, there are many different forms of astronomers, as you must know by now, and one of the groups is people who work primarily with data. Now, it used to be that the data that you had, it was very difficult to get astronomical data because it's just not available. But now in the modern era, there are larger missions, and so much more astronomical data is available. And so many of us do a lot of our work with data taken from I think mostly from space missions, the large amount of data, mostly from space missions, but from ground-based data also. And you can do many things. The key is to understand that the physics is what's important. And this is where we really need people who understand both the physics and the data analysis part, the machine learning, understanding how to access the data. But really, it all starts from the physics part. So if you're interested in astronomy from a data science point of view, I would still say that it's most important to learn the astronomy first, and then figure out how to apply the computer science part to it. I think Rajguru can add to that also.
Yeah, right. Yes, I can give you one example in where machine learning is it's going to become very popular. The solar observation of the sun, for example, there are, as I kind of mentioned in my talk, there are missions from NASA which produce large amount of data. So we have about a few terabytes of data each day from Solar Dynamics Observatory. So there are problems which you can attack from the angle of machine learning or artificial intelligence. You feed this data, a large amount of data with some physics. You need to understand some physics involved, some parameters which you can derive from this data. And then this huge amount of data, you feed it to a machine learning algorithm to predict, for example, when a flare can happen, a solar flare. So if you are observing, as the movie which Piali Chatterjee showed, that we observe the sun in magnetic field, we produce these magnetograms every 1 minute. So there's huge amount of data. So, the magnetic fields cause the flares. So there is a very clear application of machine learning. There are a lot of papers that have been already published to train machine learning algorithms to predict flares, and so that's just one example. So similar examples they're in all over astronomy. You might have heard about Google. Google scientists applied some machine learning algorithms and found a planet, an exoplanet, from the Kepler data. So yeah, I mean, there's a big role for data scientists in astronomy, actually.
Okay, thank you, Rajguru. So last question is about the winter school. Somebody is asking about the winter school, IIA winter school. Omkar Gupte, you can ask, and then that will be the last.
So the winter school, I think PLE can answer that. Are you there, PLE?
Yeah, actually, the winter school is not, an astrophysics, as in covering all areas of astrophysics, but that is basically focusing on solar physics. So till now, I think we have organized some 3 or 4. I have been participating in 3 or 4 winter schools, and they are specifically organized at the Kodaikanal Solar Observatory, where we also put in some observational and hands-on sessions for students to, go around and look at the telescopes, adjust some optics and things like that. But since the pandemic started, we haven't taken it online like the IIA summer school, which, Prava has done it very nicely. But if, such a situation continues even longer, maybe we will also think about taking the solar physics winter school online, but we haven't done so far.
Okay, so on that note, I think it is time to close the school. Thanks to all the lecturers, tutors, and the participants. I think the participants were also amazing. Lots of wonderful questions.
Thanks to the organizer also. Professor Prabhavati also did a great job, and hope that every year there will be such type of summer school. Even if it continues with online, then we can accommodate in future more students. This time it was 250, I think 220 to 250. Hope that we can accommodate more people in future. So great job, Prabha.
Thank you.
Thanks to Prabha.
Yeah, thank you, Prabha.
Yeah, thank you, Prabha.
Thanks, Prava, and
Thanks,
everybody
Prava.
else, also
Yeah.
the student volunteers.
Yeah, we are having a pizza party now, so I should leave. Thank you.
Thank you, Prabha.
Thank you. Bye.